What if everything you thought you knew about ancient history was incomplete? Picture this: massive stone structures built with such precision that not even a razor blade can slide between the joints, concrete that actually grows stronger with time, and intricate devices that tracked celestial movements with astonishing accuracy. These aren't scenes from a science fiction movie. They're real, tangible remnants of civilizations long gone, yet their technological prowess leaves modern experts scratching their heads in wonder. We often imagine the past as a simpler time, a linear progression from primitive tools to advanced machinery. But what if the story is far more complex and far more fascinating than we've been led to believe? Today, we're setting out on a journey to explore 29 lost technologies of the ancient world that continue to baffle historians, archaeologists, and scientists around the globe. These aren't just curiosities or minor puzzles. They are profound mysteries that challenge the very foundations of what we assume about human innovation and capability. Think about the Romans, who engineered concrete that has survived 2,000 years in seawater while our modern versions crumble within decades. Or the ancient Egyptians, who quarried, transported, and assembled granite blocks weighing as much as 700 tons with a level of precision that seems almost supernatural. How did they achieve such feats without the advanced machinery we take for granted today? The answers, or lack thereof, invite us to reconsider not only how we view ancient peoples, but also what might be possible when human creativity meets necessity. This video is more than a list of intriguing artifacts. It's an invitation to see history through a new lens, one filled with wonder, curiosity, and a deep respect for the ingenuity of those who came before us. As we uncover these 29 marvels, you'll find yourself questioning long-held assumptions and marveling at achievements that somehow slipped through the cracks of conventional historical narratives. Whether it's ancient energy devices, forgotten metallurgical secrets, or architectural techniques that defy explanation, each discovery pulls us deeper into a story of human potential that transcends time. So settle in and open your mind. You're about to embark on an exploration that just might change how you see the past, the present, and the incredible possibilities of tomorrow. To grasp the sheer brilliance of these ancient achievements, we need to step back and view them not as isolated miracles but as the products of their time. We often fall into the trap of imagining these civilizations in a vacuum, picturing the pyramids rising from an empty desert or Roman aqueducts cutting through an uninhabited landscape. But the reality was a dynamic, often demanding world. The Egyptians weren't just building tombs, they were forging a divine kingdom along a temperamental river that could either nourish their society or drown it, driving them to create lasting monuments to their gods and pharaohs that could withstand the test of millennia. The Romans, engaged in massive expansion, needed to supply their vast armies and growing cities with fresh water, durable roads, and formidable defenses, leading to breakthroughs in civil engineering that still form the backbone of modern infrastructure. What's truly remarkable is the shared drive for innovation across these disparate cultures, separated by oceans and mountains. The Maya in the dense rainforests of Mesoamerica developed a complex calendar system and understood celestial cycles with a precision that was crucial for their agriculture and religious ceremonies. Meanwhile, on the other side of the world, the Greeks were laying down the principles of philosophy and geometry, tools that would become the very language of science and engineering. This wasn't a coincidence. Each civilization, faced with its own unique set of environmental pressures, resource limitations, and spiritual beliefs, was compelled to push the boundaries of what was possible. They didn't have microchips or combustion engines, but they possessed a deep, intuitive understanding of mathematics, physics, and the natural world around them, knowledge that was painstakingly observed, recorded, and passed down through generations. This interconnected web of ancient innovation suggests a level of sophistication that modern history is only beginning to fully appreciate. Trade routes, often far more extensive than we assume, acted as conduits for not just goods but for ideas. Knowledge of astronomy, metalworking, and construction techniques could travel, be adapted, and be refined by different cultures. This context transforms these lost technologies from curious footnotes into profound evidence of a vibrant and intellectually restless ancient world. They represent the pinnacle of human problem solving with the tools and materials available at the time, achievements that were hard-won and deeply valued. By seeing their work within this richer, more complex historical landscape, the mysteries we are about to explore become even more compelling. They stop being mere puzzles and instead become windows into the minds of our ancestors, reminding us that the drive to create, to understand, and to build something lasting is a fundamental part of the human story. And that restless drive to innovate, to map the heavens and track the cycles of time, brings us to one of the most stunning and perplexing artifacts ever pulled from the ancient world, the Antikythera Mechanism. Discovered over a century ago in the wreckage of a Roman cargo ship off the coast of a tiny Greek island, this corroded lump of bronze and wood sat unnoticed in a museum for decades before anyone realized it was anything special. It wasn't until painstaking X-ray and imaging technology became available that researchers could see past the calcified outer crust and peer inside. What they found was nothing short of revolutionary, an incredibly complex clockwork machine consisting of at least 30 interlocking bronze gears, precisely calibrated dials, and intricate inscriptions. This wasn't a simple navigational tool or a decorative object. It was a sophisticated mechanical computer, a device of such genius that it fundamentally rewrites our understanding of ancient Greek science and engineering. The purpose of this hand-cranked device was to model the universe. By turning a handle on its side, an operator could advance the mechanism through time, watching as tiny celestial bodies moved across a dial that represented the sky. It could predict the positions of the sun and the moon with remarkable accuracy, showing their movements against the backdrop of the zodiac. It even accounted for the moon's slightly irregular orbit, using a clever pin and slot gear system to mimic its speeding up and slowing down. But its functions went far beyond basic astronomy. This single machine could forecast solar and lunar eclipses, track the cycles of the ancient Olympic Games, and even model the irregular motion of the known planets. It was, in essence, a compact, portable planetarium, a tangible simulation of cosmic order that could be held in your hands. The existence of such a device around 100 years before the Common Era is what makes it so utterly baffling. We have no other artifacts from the Greco-Roman world that even come close to its mechanical sophistication. The knowledge of gearing required to build it, the precise calculations of tooth counts and gear ratios to accurately represent celestial cycles, was thought to be lost to history for another 1,000 years. Nothing of comparable complexity would appear again until the astronomical clocks of medieval Europe in the 14th century. So how did the ancient Greeks, without the benefit of precision machining tools or advanced metallurgy, create something so advanced? The craftsmanship is so fine, so miniaturized, that experts believe it must have been created by a master artisan working within a long-established tradition. This wasn't a one-off prototype or a lucky accident. It was almost certainly a product of a school of thought, a lineage of mechanical knowledge that has since vanished without a trace. This leads to the most tantalizing question of all: who made it, and what else did they create? The mechanism itself is a window into a lost world of ancient technology that classical texts barely mention. The writings that have survived from that era speak of wondrous automated devices and theatrical machines, but they were always considered fanciful exaggerations or simple novelties. The Antikythera Mechanism proves that the Greeks possessed the engineering capability to turn those concepts into reality. It forces us to wonder what other incredible inventions were lost to time, consumed by fires, or sunk to the bottom of the sea. Was this mechanism a unique treasure, or was it merely one of many such devices, a single surviving example of a technology that was once more widely understood? The silent, corroded gears of the Antikythera Mechanism hold their secrets tightly, offering a humbling reminder that the past may have been far more technologically brilliant than our history books have ever dared to suggest. If the intricate gears of the Antikythera Mechanism represent a peak of ancient precision engineering, then the monumental structures of Rome showcase a mastery of materials on a truly epic scale. While we marvel at their arches and aqueducts for their grandeur, the real magic is hidden in the very fabric of the stone, a seemingly humble mixture that has proven to be one of history's most durable building materials. Walk through the Roman Pantheon today, and you stand beneath the largest unreinforced concrete dome in the world, a structure that has weathered nearly 2,000 years of elements, earthquakes, and upheavals without a single crack compromising its integrity. Compare that to many of our modern concrete structures, which often show significant decay within just 50 years, and the mystery deepens. How did the Romans achieve such longevity while we struggle with crumbling infrastructure? The secret lies in a recipe that was, for the most part, lost with the decline of the Roman Empire. Our modern Portland cement-based concrete is a relatively simple mixture of cement, water, and aggregates like sand and gravel. The Romans, however, worked with a far more sophisticated formula. Their key ingredient was a specific type of volcanic ash, known as pozzolana, which they sourced from deposits around the Bay of Naples. They would mix this ash with lime and seawater, and then incorporate chunks of rock or brick. This combination initiates a remarkable chemical process. The lime and the pozzolana react with the seawater to form crystals that are incredibly stable and resistant to corrosion. But the most astonishing property is what happens over centuries. When tiny cracks do begin to form from the immense stress of time, moisture seeps in and reacts with the leftover lime and volcanic material, forming new minerals that actually fill the crack and heal the wound. This isn't just passive durability, it's an active, self-healing technology. For a long time, historians and engineers believed this was a happy accident, a fortunate combination of locally available materials that the Romans themselves didn't fully understand. But recent scientific analysis has turned that assumption on its head. Studies using advanced microscopes have revealed that the Roman mixture produces an exceptionally rare mineral called aluminous tobamorite within the lime class. This mineral, which forms in the lime as it ages, is a key component in the concrete's strength and its self-healing capabilities. The Romans may not have had the vocabulary of modern chemistry, but their empirical trial-and-error methods led them to a formula that we are only now beginning to decode with our most advanced tools. They weren't just lucky, they were brilliant materials scientists who understood the properties of their local resources on an intimate level. The implications of this lost knowledge are profound. Consider the sheer volume of modern construction that relies on concrete, a material whose production is a major contributor to global carbon dioxide emissions. If we could successfully reverse engineer and adapt the Roman recipe, we could create a new generation of ultra-durable, sustainable building materials that would not only last for millennia, but would also have a significantly lower environmental cost. The quest to unlock this ancient secret is now a major focus of research, with scientists around the world experimenting with different volcanic ashes and mineral combinations, trying to replicate the Roman success. It's a humbling thought that the path to a more sustainable future in construction might be found by looking backward, by rediscovering a technology that was commonplace 2,000 years ago. It forces us to ask what other recipes for resilience and longevity we have carelessly discarded in our relentless pursuit of the new. While Roman concrete demonstrates an ancient mastery of materials on a grand architectural scale, another civilization perfected a different kind of alchemy, one that transformed metal into legendary weapons of war. The fame of Damascus steel blades is etched not just in history, but in the very metal itself, with its mesmerizing, watery patterns that look like a frozen storm. These weren't merely decorative, they were the superweapons of their era, forged from roughly 300 CE onward and coveted by warriors from the Crusaders to the Mughals. Historical accounts describe these swords as possessing almost supernatural qualities. They were said to be flexible enough to bend 90 degrees without breaking, yet so sharp and resilient that they could cleave through an opponent's helmet, armor, and even another inferior blade, all while maintaining a razor-sharp edge. This combination of hardness and flexibility is a paradox that modern metallurgists still struggle to replicate, making the loss of this technique one of history's most frustrating technological dead ends. The secret didn't lie in the skill of the blacksmith alone, but in the very Chinese letter, or raw material they started with. Damascus steel was forged from a special type of high-carbon steel ingot known as wood steel, which originated in India. These ingots were crucible steel, meaning the iron was melted in a closed clay pot with carbon-rich materials like wood or leaves, allowing the carbon to dissolve evenly into the iron in a controlled environment. But the true magic happened during the incredibly intricate forging process. The blacksmith would slowly heat and hammer the ingot, folding it over upon itself repeatedly. This labor-intensive process wasn't just about shaping the metal, it was about manipulating its internal crystalline structure at a microscopic level. The specific trace elements present in the original Indian ore, particularly vanadium, molybdenum, and other impurities, combined with this careful thermal cycling to create a unique nanostructure within the blade. Under a modern microscope, the mystery begins to unravel, yet deepens all the same. The distinctive wavy pattern isn't merely etched on the surface. It is the visible evidence of a complex matrix of ultra-hard iron carbide particles arranged in bands within a softer, more flexible steel background. Think of it as a natural composite material. The hard carbides provide the incredible sharpness and edge retention, while the softer steel matrix allows the blade to absorb tremendous impacts without shattering. This is what gave the swords their legendary durability. The precise temperature controls during heating and the very specific rate of cooling were absolutely critical to forming these structures. It was a recipe where even a slight deviation in the process would result in a blade that was too brittle or too soft. A balance that ancient smiths mastered through generations of meticulously guarded, hands-on knowledge. So why was this knowledge lost? The most likely explanation is a breakdown in the supply chain. The production of true Damascus steel relied on those specific wood ingots from particular mines in India. As trade routes shifted or those specific ore deposits were exhausted, the raw material needed for the recipe vanished. Without the correct starting material, later blacksmiths could not replicate the process, no matter how skilled they were. The knowledge, passed down through apprenticeships rather than written manuals, faded away within a few generations. By the 18th century, the art was completely lost, leaving behind only the legendary blades themselves. Modern attempts to recreate Damascus steel, even with our advanced electron microscopes and controlled atmosphere furnaces, have produced blades that may visually mimic the pattern through acid etching or different forging techniques, but they consistently lack the same legendary mechanical properties. The nanoscale carbide structures of the originals remain unique. This isn't just a lost recipe, it's a lost material science paradigm, a testament to the fact that ancient innovators could achieve results through artisanal skill and deep empirical observation that our technology still cannot quite match. From the forging fires that created legendary blades to the alchemical mastery of Roman concrete, we've seen how ancient technologies often revolved around controlling and manipulating the physical world. But perhaps no lost invention embodies the raw, terrifying power of ancient science more than Greek fire, a weapon so formidable it could literally set the sea ablaze. Used primarily by the Byzantine Empire from around the 7th century, this incendiary substance was the ultimate naval weapon of its era, a tool that could single-handedly decide the outcome of a sea battle and protect Constantinople from numerous sieges for centuries. Imagine the sheer horror of being a sailor on an enemy ship, watching as a stream of liquid fire was projected from a Byzantine dromon, a flame that clung to everything it touched: wood, sails, skin, and most terrifyingly, the water itself. This wasn't a normal fire that could be doused with buckets of seawater. It was a hellish concoction that seemed to burn with a mind of its own, creating an inescapable inferno that consumed entire fleets. The secret of Greek fire, known to the Byzantines as sea fire or liquid fire, was so closely guarded that it remains one of history's most impenetrable secrets. The exact formula was known only to a very select few, allegedly even within the imperial family, with knowledge passed down from one emperor to the next. Contemporary descriptions and modern analysis point to a likely base of crude petroleum or naphtha, sourced from natural oil seeps around the Black Sea. This volatile liquid was then almost certainly mixed with other chemicals to create its infamous properties. Quicklime, which ignites upon contact with water, is a prime candidate, explaining why the fire seemed to intensify when sailors tried to extinguish it with water. Other potential additives include resin or pitch to make it sticky, sulfur to lower its ignition temperature, and saltpeter to introduce an oxidizing agent that would allow it to burn even underwater. The precise combination and ratios, however, are what we have never been able to rediscover. The delivery system was as innovative as the substance itself. It wasn't simply thrown in pots. It was deployed with terrifying efficiency through a complex pressurized siphon called a siphonarios. This bronze tube, often mounted on the prow of a ship, could project the fiery stream over a significant distance with a roar that was said to resemble thunder. Some accounts describe the siphons being mounted on the sides of ships, or even on portable platforms for use on land. For smaller-scale assaults, clay grenades filled with the mixture were also used, hurled by hand or catapult to spread the fire among enemy ranks. The psychological impact cannot be overstated. To an enemy who believed the Byzantines commanded the very elements, facing Greek fire was like facing a supernatural force, a weapon sent by God to defend the empire. This psychological warfare was arguably as powerful as the physical destruction it caused. The absolute secrecy surrounding its manufacture is a fascinating case study in ancient intellectual property protection. The Byzantine emperors treated the formula not just as a military asset, but as a divine gift, a state secret on par with the crown jewels. The knowledge was compartmentalized. The chemists who brewed it likely knew only their part of the process, while the engineers who operated the siphons knew only how to use it. This intense secrecy ultimately led to the technology's complete disappearance. As the Byzantine Empire declined, the carefully guarded chain of knowledge was broken. By the time Constantinople fell to the Ottomans in 1453, the secret had been lost for centuries. Modern attempts to recreate Greek fire have produced flammable liquids, but nothing that matches the terrifying description of a substance that water could not quench, that could be sprayed in a continuous stream, and that burned on the surface of the waves. We are left with a chilling question. What other powerful inventions capable of altering the course of history were lost because their creators guarded their secrets too well, taking them to the grave without a single written record? The enigmatic flame of Greek fire continues to flicker in the annals of history, a brilliant and terrifying reminder of how the drive to protect an advantage can sometimes lead to the permanent extinction of knowledge itself. Moving from the controlled fury of Greek fire to the silent, sprawling artistry of the Peruvian desert, we encounter a mystery not of destructive power, but of profound spiritual and scientific expression. The Nazca lines are a breathtaking anomaly, a gallery of colossal artwork etched into the earth itself, whose true impact can only be fully appreciated from the vantage point of the gods. Created by the Nazca culture between 500 BCE and 500 CE, these geoglyphs are not mere scratches on the surface. The Nazca people carefully removed the top layer of dark, sun-baked pebbles to reveal a lighter, contrasting sand beneath, creating lines that have endured for over 2 millennia in one of the driest and most windless climates on Earth. The resulting figures are staggering in their scale and variety: a hummingbird with wings outstretched, a spider with perfectly proportioned legs, a monkey with an intricately coiled tail, and a whale swimming across a desert plateau. Some of these designs stretch to over 1,200 feet in length, larger than the biggest modern aircraft carriers, yet they maintain a stunning clarity and precision that defies their simple method of construction. The central, most perplexing question is how and why they were made with such accuracy, given that their creators would never have seen the complete, unified image. From ground level, the lines appear as shallow grooves or paths. The full, magnificent form of the spider or the condor is utterly invisible. This has led to a fascinating array of theories attempting to solve the puzzle of their purpose. One prominent idea suggests they functioned as a massive astronomical calendar, with certain lines aligning with the solstice sun or key constellations, marking crucial dates for planting and harvesting in an unforgiving environment. Others propose they were sacred pathways, walked during religious rituals to invoke the deities represented by the animal figures, perhaps to pray for life-giving water. A more speculative theory even suggests they were landing strips or signals for extraterrestrial visitors, though this is widely dismissed by mainstream archaeologists who point to the very human ingenuity evident in their construction. The real marvel lies in the practical execution. Without aerial views, advanced mathematics, or even the wheel, the Nazca people achieved near-perfect geometric precision. Researchers believe they used a system of scaled models. A small master diagram could have been laid out on a grid of stakes and strings, and then scaled up to a massive size by using a larger grid on the desert floor. Simple tools like wooden stakes and ropes would have been sufficient to transcribe the curves and straight lines across vast distances. Maintaining the proportions over hills and uneven terrain required a sophisticated understanding of surveying, likely using a series of sighting posts to keep the lines straight and the angles true. This was not a haphazard effort. It was a monumental project of coordinated labor and planning, a testament to a highly organized society with a shared, powerful vision. Yet the most enduring mystery may not be the how, but the why. Why invest such immense communal effort into creating art that you could never fully see? The answer likely lies in the spiritual worldview of the Nazca people. In a landscape where water was the difference between life and death, these giant figures may have been offerings to the gods of the sky and the earth, desperate pleas for rain and fertility, meant to be seen not by humans, but by the deities looking down from the heavens. The lines could have been a form of sacred landscape, a way to connect the earthly realm with the celestial one, transforming the barren desert into a temple without walls. This shifts our perspective from seeing the Nazca lines as a technical puzzle to understanding them as one of humanity's most ambitious acts of faith, a permanent prayer etched into the very skin of the planet, forever waiting for a divine audience. While the Nazca lines represent a vast, visible testament to ancient ingenuity aimed at the heavens, another discovery suggests a more intimate and equally baffling form of knowledge, one that dealt with an invisible force we now take for granted. In the basement of the National Museum of Iraq in Baghdad sits a collection of rather unassuming-looking artifacts, a handful of small clay jars, each about the size of a fist. They were excavated in the 1930s from a 2,000-year-old site just outside the city, dating them to either the Parthian or Sassanid eras, roughly between 250 years before the Common Era and 250 years after. To the untrained eye, they appear to be nothing more than ancient storage vessels, perhaps for holding scrolls or precious oils. But upon closer inspection, their construction reveals a design that is deeply peculiar and to some profoundly revolutionary. Each jar contains a rolled copper cylinder sealed at the bottom with asphalt, and within that cylinder sits an iron rod, isolated from the copper by that same asphalt plug. This isn't the design of a simple container, it is the precise architecture of a chemical cell. The stunning implication, first proposed by a German archaeologist in the 1940s, is that these objects could be ancient electric batteries. The hypothesis is simple yet electrifying. If the jar were filled with an acidic electrolyte, something as common as vinegar or citrus juice, a chemical reaction would occur. The acidic liquid would interact with the two different metals, causing electrons to flow from the iron rod to the copper cylinder through the external medium. This would create a small but measurable electric current, around 1 volt of electricity, roughly the same output as a modern double-A battery. Researchers who have built replicas have confirmed it works exactly as theorized. The current is small, to be sure, but it is undeniably present. This raises the immediate and thrilling question: what on earth would a 2,000-year-old civilization need with a portable source of electricity? The most plausible theory points to the art of electroplating. The region was known for its exquisite gold and silver work, and artisans may have discovered that by connecting a series of these Baghdad batteries together, they could create a stronger current capable of a process called gilding. An object made of a base metal like silver could be placed in a solution containing gold salts. When connected to the battery, the electric current would cause the gold particles to slowly and evenly bond to the surface of the object, creating a beautiful, durable, and convincing gold coating. This would have been a form of magic, transforming ordinary metal into what appeared to be solid gold through a process that was utterly invisible and must have seemed miraculous. Another compelling, though more speculative, use could have been for medical purposes. Ancient Greek and Roman texts describe the use of electric fish to administer shocks for pain relief. It's conceivable that a healer or priest might have used the gentle, tingling current from such a device for a form of electrotherapy, perhaps to soothe muscle pain or to create a startling sensory experience during a religious ritual. Of course, not everyone is convinced by the battery theory. skeptics offer alternative explanations, suggesting the jars were simply secure storage for sacred scrolls, with the iron and copper acting as protective rods to keep the precious papyrus or parchment from decaying. The asphalt seal would have provided an airtight environment, preserving the contents. This is a reasonable, mundane explanation, but it doesn't fully account for the specific choice of two different metals isolated from each other inside the vessel, a design that seems almost intentionally engineered to create a chemical reaction. The truth is, we may never know for certain. The objects themselves offer no written instructions or clear context. What makes the Baghdad Battery so captivating is not that it definitively proves ancient mastery of electricity, but that it represents a brilliant, glimmering possibility. It is a tantalizing what-if that sits at the crossroads of archaeology and speculation. Its very existence forces us to consider that a thread of experimental science, one that understood the principles of electrochemistry, might have existed and then been completely snipped from the tapestry of history. The loss of this potential technology is a quiet tragedy, a forgotten chapter that makes us wonder what other fundamental forces of nature ancient innovators might have glimpsed, only to have their understanding fade away before it could ever truly spark a revolution. If the Baghdad Battery hints at a lost understanding of invisible energy, the stonework of the Incas presents a mystery of a different kind, one of immense physical mass manipulated with almost impossible precision. High in the Andes, the ruins of sites like Sacsayhuamán and Ollantaytambo are not just archaeological wonders, they are a direct challenge to our assumptions about ancient construction. The most iconic example is the famous 12-angled stone in Cusco, a massive block carved with 12 perfectly interlocking sides that seamlessly dovetail into the surrounding wall. But this is just one piece of a much larger puzzle. The Incas built with a technique known as ashlar masonry, constructing walls from massive, irregularly shaped polygonal stones that fit together like an intricate, three-dimensional jigsaw puzzle. The fit is so impossibly tight that, as the saying goes, you cannot slide a razor blade, let alone a piece of paper, between the joints. This was achieved entirely without mortar. The stones themselves are the structure, and they have withstood over 500 years in one of the most seismically active regions on the planet. The process of how they built these marvels is a deep and enduring mystery, starting with the quarrying of the stone itself. The Incas did not have iron or steel. Their hardest metal was bronze, an alloy too soft to effectively cut and shape granite and andesite. They lacked wheeled vehicles or draft animals strong enough to haul these multi-ton blocks up and down the steep mountain valleys. At sites like Ollantaytambo, the quarry is located on a mountainside across a river valley and nearly 1,000 feet above the temple complex. Transporting 50-ton stones down one mountain, across a rushing river, and up another mountain is a logistical nightmare that modern engineers still struggle to explain. The prevailing theory suggests they used an army of laborers with ropes, levers, and log rollers, moving the stones incrementally along carefully prepared earthen ramps. It was a monumental feat of organized human effort, a testament to the power of the Inca state to command and coordinate its people. Then comes the even greater mystery, the shaping. How did they achieve those flawless, complex joins? We have found very few of their stone tools, typically round hammerstones made of even harder rock. The conventional explanation is that they pounded the stones into shape through patient, relentless pecking, then polished the surfaces with sand and water. This is plausible for creating a flat face, but it utterly fails to explain the intricate, concave and convex surfaces that interlock with their neighbors with sub-millimeter precision. The stones often feature nubs, grooves, and subtle protrusions that seem to have been used as handles or alignment guides during construction. To achieve this with simple hammerstones would require an almost supernatural level of skill and an unimaginable amount of time for each block. This has led to more speculative yet fascinating alternative theories. Some researchers point to the possibility that the Incas discovered a way to soften the stone using a plant-based chemical compound, a lost botanical formula that could temporarily make the rock malleable like clay. While there are local legends that speak of such a juice, no such plant has ever been identified. Another compelling idea involves the use of sound or vibration. Could specific resonant frequencies produced by chanting or striking the rock with precise tools have been used to fracture the stone along desired planes? It's a tantalizing thought, but one for which there is no archaeological evidence. The most likely explanation is that the Inca stonemasons were simply masters of their craft. They developed an incredibly sophisticated eye for measurement and geometry, perhaps using clay or wooden templates to map out the complex negative spaces each new block needed to fill. It was a technology of knowledge and skill, not of advanced machinery, passed down through generations of artisans who turned a brutally difficult medium into a form of high art. The true genius of their method, however, is revealed not in times of calm, but during the earthquakes that frequently shake the Andes. Mortar-based walls are rigid. When seismic waves hit, they crack and crumble. The Inca walls, however, are designed to dance. During a quake, the tightly interlocked stones in a polygonal wall will vibrate and shift minutely against each other, dissipating the enormous energy of the earthquake throughout the entire structure. When the shaking stops, the stones simply settle back into their original positions. This is not a lucky accident. It is brilliant, intentional seismic engineering. The Incas understood their environment and designed their cities to become one with the living, moving earth beneath them. Their structures have survived centuries of tremors that have reduced later Spanish colonial buildings to rubble, a silent and enduring lesson from the past on how to build in harmony with nature. The loss of their precise techniques is more than just a historical puzzle. It is the disappearance of a profound architectural philosophy that we are only now, in our modern search for earthquake-resistant design, beginning to fully appreciate and strive to relearn. Leaving behind the silent, unmoving stones of the Andes, we now set sail into the stormy, cloud-shrouded waters of the North Atlantic, where another civilization mastered their environment through a technology that seems pulled from the pages of a fantasy novel. The Vikings, those legendary seafarers, accomplished feats of navigation that still inspire awe. They crossed thousands of miles of open ocean to reach Iceland, Greenland, and even the shores of North America half a millennium before Columbus, all without the aid of a magnetic compass. How did they traverse such featureless and treacherous seas under often overcast skies, especially during the long, dark polar winters when the sun might not be seen for weeks? The answer may lie in a mysterious object mentioned in the Norse sagas, the Solarstein or Sunstone. This wasn't a mythical artifact in a magical sense. Medieval texts refer to it as a tangible crystal used for navigation. The most famous account comes from the saga of Saint Olaf. On a deeply overcast day, the king needed to locate the sun to verify his position. He asked a follower to hand him the sunstone, held it aloft, and by looking through it, was able to pinpoint the sun's location behind the thick blanket of clouds. For centuries, this story was dismissed as a charming legend, a narrative device rather than a historical record. But in recent decades, a compelling scientific hypothesis has emerged, turning this myth into a plausible, brilliant technology. Researchers now believe the sunstone was likely a crystal of Iceland spar, a transparent form of calcite or perhaps cordierite, minerals common in Scandinavia. These crystals possess a fascinating optical property known as birefringence or double refraction. The science, while complex in its details, is stunningly simple in its application. Even when the sun is completely hidden by cloud or fog, a small patch of the sky is still slightly brighter than the rest, indicating the sun's general position. However, the human eye is notoriously bad at pinpointing this subtle gradient of light. A crystal like Iceland spar changes the game entirely. When you rotate such a crystal while pointing it toward the sky, the light passing through it splits into two beams. The key is that the intensity and polarization of these two beams change depending on the crystal's angle relative to the hidden sun. By rotating the stone until the two beams appear to be of equal brightness, a navigator can accurately determine the exact azimuth of the sun, even when it is completely invisible to the naked eye. It's a natural, handheld GPS that operates on the fundamental principles of light physics. Experimental archaeology has put this theory to the test with remarkable success. In one notable study, a team of researchers used a calibrated piece of Iceland spar to take bearings on the sun under overcast conditions. They found they could determine the sun's position with an accuracy of within a single degree, a level of precision more than sufficient for ocean navigation. This tool, used in conjunction with other Viking navigational knowledge, like reading the patterns of waves, wind, and the flight paths of birds, would have provided an incredibly reliable method for holding a course. A navigator could take a reading with the Sunstone, mark the sun's direction on a dial, or simply mentally note it, and then use that fixed reference point to maintain a consistent heading for hours afterward. This technological edge would have been the difference between reaching a new world and becoming hopelessly lost at sea. Yet, for all its compelling logic, the Sunstone remains a ghost in the archaeological record. Not a single crystal has ever been found in a definitive Viking navigational context, such as aboard a wrecked longship or buried with a chieftain known as a great explorer. The only potential evidence is a small piece of Iceland spar found aboard an Elizabethan warship that sank in 1592, though its purpose on that much later vessel is unknown. This absence forces us to confront a larger, more haunting question about lost technologies. The Sunstone, if it existed, was an organic part of a vast body of knowledge passed down through oral tradition and practical apprenticeship. It required no written manual. Its use was a skill ingrained in the minds and hands of expert navigators. When that lineage of knowledge was broken, perhaps by the shift to magnetic compasses or the decline of Viking exploration, the technology didn't just become obsolete, it vanished without a physical trace, leaving behind only whispers in old stories. It stands as a powerful symbol for all the other intangible tools and techniques ancient peoples must have developed, brilliant adaptations to their world that evaporated when the last person who knew how to use them was gone, reminding us that some of history's greatest innovations leave behind not ruins but only echoes. From the Vikings' ethereal navigation with sunstones, we turn to a feat of raw physical might and celestial ambition, the raising of the Egyptian obelisks. These are not merely large stones, they are among the most audacious engineering projects ever attempted by an ancient civilization. Picture a single shaft of red granite, quarried from the earth in one perfect piece, soaring over 100 feet into the sky and weighing more than 400 tons, the equivalent of 250 modern cars. Now imagine moving that monolithic needle across miles of desert, loading it onto a barge, sailing it down the Nile, and then, in a final act of breathtaking audacity, pivoting it from a horizontal position to stand perfectly upright on a tiny stone pedestal, all without the slightest crack or flaw. This was not a rare event. It was a repeated accomplishment of the Egyptians, and the logistical ballet required to achieve it remains one of history's most captivating puzzles. The process began deep within the granite quarries at Aswan, where the stone itself presented the first monumental challenge. Workers would first identify a flawless piece of bedrock. Using nothing harder than balls of dolerite rock, they would pound out a trench around the proposed obelisk, a process of relentless, patient pecking that would have consumed countless man-hours. We know they used copper tools as well, but copper is soft against granite. It would have been more for fine-tuning and polishing than for the initial rough extraction. The real mystery lies in how they then separated this multi-hundred-ton block from the quarry floor. The prevailing theory involves driving wooden wedges into pre-cut slots and then soaking them with water. As the wood expanded, it would create tremendous pressure, theoretically cracking the stone along a clean plane. Yet, the precision of this fracture would have had to be near perfect to create the obelisk's famously smooth sides. The unfinished obelisk, still lying in its Aswan quarry, gives us a heartbreakingly clear snapshot of this process frozen in time, showing the trench and the intended form, but also a large crack that doomed the project and perhaps taught a brutal lesson in the limits of their technique. Once freed, the real test of organizational genius began, the journey to the temple. The obelisk would be dragged on a massive sledge, likely made from giant timbers from the quarry to the riverbank. This required a small army of laborers pulling on ropes, with water or mud poured ahead of the sledge to reduce friction. The scale of coordination is staggering to contemplate. Then came the river voyage, a feat of nautical engineering that seems almost impossible. A specially built, enormously strong barge would be floated next to the obelisk, which was then carefully pulled aboard until its immense weight rested along the vessel's centerline. The slightest miscalculation in loading would have capsized the ship instantly. Historians believe these barges were built with a much wider beam than typical Nile boats to provide stability, and they may have been accompanied by a flotilla of other ships lashed alongside to act outriggers, creating a stable, catamaran-like platform for this precious, staggering cargo. But the most dangerous moment, the true climax of the entire endeavor, was the raising. How do you lift the end of a 400-ton stone needle and pivot it to a 90-degree angle, setting its base precisely into a small prepared foundation slot, without it slipping, cracking, or crushing the workers below? The Egyptians left us no manuals, only the silent, triumphant results. The most widely accepted theory involves the construction of a massive earthen ramp next to the waiting pedestal. The obelisk, still on its sledge, would be dragged up this ramp until its base was positioned directly over the foundation hole. The back of the obelisk would then be slowly lowered by gradually removing sand from a chamber beneath the ramp, allowing gravity to pull the base downward into its slot while the top was pivoted upward with ropes and levers. It was a delicate dance of counterweights and controlled descent, an operation requiring flawless communication and nerves of steel from every single participant. The margin for error was zero. Beyond the sheer physical achievement, the purpose of these obelisks reveals a mind-bending fusion of engineering, astronomy, and religion. They were not just monuments, they were instruments, covered in electrum, a shimmering alloy of gold and silver. Their tips were designed to catch the first and last rays of the sun, flashing like beacons across the land. They were precisely aligned to function as giant sundials and to mark significant celestial events like solstices. In the sacred geometry of the temple complex, an obelisk was a petrified ray of sunlight, a direct connection between the earth and the heavens, a symbol of the primeval mound from which the creator god emerged. The fact that they achieved this spiritual and astronomical precision through a colossal feat of earthly logistics is their most enduring legacy. They stand today not just as tributes to pharaohs, but as timeless proof that human imagination, when combined with impeccable organization and a deep understanding of the physical world, can achieve the seemingly divine. While the Egyptians and Incas demonstrated a mastery of stone and the Vikings harnessed the hidden sun, an inventor in ancient China turned his attention to the very ground beneath his feet, seeking to understand its most violent and unpredictable movements. In the year 132 of the Common Era, during the Han Dynasty, the brilliant polymath Zhang presented the court with a device that must have seemed like something from the realm of magic, the world's first seismoscope. This was not a simple instrument. It was an object of breathtaking artistry and profound scientific ambition. Cast in bronze, it took the form of a large, ornate urn, perhaps as tall as a man, surrounded by 8 dragons, each facing a cardinal or intercardinal direction: north, south, east, west, and the points in between. Below each dragon, with its mouth agape, sat a corresponding bronze frog, its own mouth open in anticipation. The principle behind its operation was as elegant as its appearance was magnificent. Inside the vessel, modern researchers believe, hung a heavy inverted pendulum. When seismic waves from a distant earthquake rippled through the earth, they would cause this pendulum to swing. However, the internal mechanism was ingeniously designed to amplify and direct this motion. It is thought that the pendulum's swing would trigger a lever apparatus connected to one of the 8 dragons' heads. This action would release a heavy bronze ball clutched within the dragon's jaws, causing it to drop with a loud, unmistakable clang directly into the mouth of the frog waiting below. The direction indicated by the frog that caught the ball was the general direction from which the earthquake's tremors had originated. This provided court officials with crucial, early information about where a disaster had struck, potentially enabling them to send aid to affected regions long before messengers could arrive on foot. The historical records attest to its startling accuracy. The most famous account describes an instance when a ball dropped from the dragon facing west, yet no tremors were felt in the capital city of Luoyang. Skeptics dismissed it as a false reading, until several days later a messenger arrived from a village hundreds of miles to the west, reporting the devastation of a massive earthquake. The device had not only detected the quake but had correctly identified its direction from an impossible distance. Modern engineers and seismologists who have attempted to recreate Zhang Heng's device based on the scant historical descriptions have been met with both admiration and frustration. Their functional models confirm that the basic principle is sound and can work with remarkable reliability. Yet the precise mechanical details of the internal mechanism, the exact arrangement of levers, hinges, and catches that would allow it to be so sensitive and yet so specific remain a subject of intense debate and speculation. The original design was lost, a secret that seemingly died with its creator. This loss is a profound one because Zhang Heng's seismoscope represents far more than just a clever gadget. It embodies a revolutionary shift in thinking. In an era when earthquakes were widely interpreted as signs of heavenly displeasure or cosmic imbalance, this device provided a physical, mechanical explanation. It suggested that these terrifying events were natural phenomena that could be measured, understood, and perhaps even predicted. It stands as a monumental achievement in geophysics, predating the development of modern seismology in Europe by over 1,500 years. It forces us to confront a deeply intriguing possibility. If one ancient scientist could conceive of and build such an effective early warning system, what other disaster detection technologies might have been developed in antiquity and then lost to the relentless erosion of time? Were there other Zhang Hengs in other cultures whose brilliant contraptions to monitor volcanoes, tsunamis, or storms simply rusted away without a trace, leaving behind only unverified legends? His seismoscope is a powerful reminder that the drive to protect society, to harness science as a shield against nature's fury, is an ancient and noble pursuit, one whose forgotten chapters we are only just beginning to rediscover. This same drive to measure and understand the cosmos, to find order in the cycles of the heavens, found one of its most complete and elegant expressions not in the Old World, but in the rainforests of Mesoamerica. The ancient Maya possessed a conception of time that was so intricate, so mathematically profound, that it stands as a monumental intellectual achievement, completely independent of the astronomical traditions developing in Europe and Asia. Their calendar system wasn't just a tool for marking days. It was a complex, interlocking set of cycles that formed the very backbone of their civilization, governing agriculture, religion, and royal authority with a precision that seems almost impossible without modern instruments. At its heart were not one, but three distinct calendars operating in unison, a bit like interlocking gears of different sizes. The first, the 260-day Tzolk'in, or sacred round, was the cornerstone of ritual life. This wasn't based on any obvious astronomical cycle like the sun or moon. Instead, it was a combination of 20-day names and 13 numbers, creating a 260-day cycle that was believed to be charged with sacred energy. Each day had its own patron spirit and divine associations, and priests would use this calendar to determine the most auspicious times for everything from planting crops and going to war to crowning a new king and conducting marriage ceremonies. It was a divinatory tool, a way of aligning human activity with the perceived rhythms of the spiritual world. Running concurrently was the 365-day Hab, or vague solar year. This was closer to our modern calendar, consisting of 18 months of 20 days each, plus a short, ominous period of 5 unlucky days known as the Wayeb at the end. The Hab tracked the seasons, crucial for an agricultural society whose survival depended on knowing exactly when the rains would arrive and when to plant their staple crop, maize. But here's where the Maya genius truly shines. They were acutely aware that the true solar year is actually about 365.2422 days long. They understood that their Hab would slowly drift out of sync with the actual solar year over time. Rather than ignoring this, they meticulously calculated this drift and made precise corrections, a concept similar to our leap year but far more complex in its execution. The real masterpiece, however, was the calendar round, the combination of the Tzolk'in and the Hab. Because 260 and 365 have a least common multiple of 18,980, it would take exactly 52 vague solar years for any specific combination of a Tzolk'in day and a Hab date to repeat. This 52-year cycle was of immense importance, marking a period of tremendous anxiety and renewal. At the end of each calendar round, the Maya feared the world might come to an end if the gods were not properly appeased with ceremonies and offerings. They would often extinguish old fires in their homes and temples and kindle new, sacred flames, symbolizing a rebirth of time itself. Yet, even this 52-year cycle was just the beginning. For recording historical events and tracking vast epochs of time, the Maya used the long count. This was a linear, rather than cyclical, count of days from a fixed starting point, a mythical date of creation that corresponds to August 11, 3114 BCE on our Gregorian calendar. The long count is what allows us to pinpoint Mayan dates with such absolute precision. They didn't count in base 10 like we do, but in a modified base 20 system. Time was counted in cycles. 20 days made a yuanal, 18 yuanals made a ton, 360 days, close to a year. 20 tons made a katon, about 20 years, and 20 katons made a bakton, about 394 years. Their inscriptions show they were comfortable working with numbers in the millions and even billions, contemplating time on a scale that is truly cosmic. Their astronomical accuracy derived from this system is what continues to stagger modern researchers. From observatories like the Caracol at Chichen Itza, Mayan priest astronomers tracked the movements of Venus with obsessive precision, calculating its 584-day synodic period to an accuracy of just 1 day every 500 years. They could predict solar and lunar eclipses and understood the precession of the equinoxes, a slow wobble in Earth's axis that takes 26,000 years to complete. This knowledge was physically manifested in their architecture. Temples were precisely aligned so that on the equinoxes, the sun would create specific light and shadow effects, like the famous descent of the serpent shadow down the steps of El Castillo. Windows in observatories were aligned to frame the extreme northern and southern setting points of Venus on the horizon. How did they achieve this with the naked eye and without complex metal tools? The answer lies in generations of unbroken observation. Dedicated scribes would record the positions of celestial bodies night after night, century after century, passing this accumulated data down through generations. They used simple but effective tools like crossed sticks to measure angles and sightlines, and they developed a sophisticated mathematics that included the concept of zero, a revolutionary abstract idea that wouldn't appear in Europe for centuries. This allowed them to perform the complex calculations needed for their predictions. The tragedy is that the vast majority of the written records containing this knowledge, the thousands of bark paper books called codices, were systematically burned by Spanish conquistadors and missionaries who saw them as pagan works of the devil. Only 4 pre-Columbian codices are known to have survived this cultural annihilation. This loss is immeasurable. We are left with the silent stone inscriptions on monuments and the breathtaking architecture, fragments of a much larger intellectual universe. The Mayan calendar system invites us to fundamentally rethink our own linear, progressive view of time. For the Maya, time was not a straight arrow moving from past to future. It was a sacred, cyclical force with patterns that repeated across vast ages, each cycle carrying its own spiritual weight and meaning. Their achievement is a humbling reminder that intellectual grandeur is not defined by the complexity of one's technology, but by the depth of one's observation, the power of one's mathematics, and the relentless human desire to find our place within the grand, orderly, and beautiful machinery of the cosmos. The mysteries of the Minoan civilization present us with a tantalizing silence, a void in our historical record that is all the more frustrating because we know the information is there, locked away in plain sight. While other cultures left behind grand monuments or intricate machines, the people of ancient Crete left us words, thousands of them etched into clay tablets, yet we cannot read a single sentence. This isn't a case of a few lost manuscripts. It's an entire library whose catalog we can see but whose stories we cannot understand. The Minoans developed not one, but 2 distinct writing systems, Cretan hieroglyphs and the later Linear A, and the failure to decipher either one means an entire dimension of this sophisticated Bronze Age society remains completely closed to us. We can walk through the labyrinthine ruins of their magnificent palace at Knossos, marvel at their vibrant, life-filled frescoes of dolphins and bull leapers, and admire their advanced plumbing and earthquake-resistant architecture, but we are ultimately just silent observers, unable to hear their own voices or learn the secrets they were so carefully recording. The physical artifacts themselves are clues to a lost world of bureaucracy and trade. The vast majority of the surviving linear tablets are not royal decrees or epic poetry. They are administrative records, inventories, lists of goods, and economic transactions. We can often recognize the logograms, the little pictures representing commodities like figs, wine, wool, or chariots, and we can see the numerical notations. But the accompanying words, the names of people and places, the verbs describing the transactions, are a maddening cipher. It's like having a spreadsheet from 3,500 years ago where you can see all the numbers and product icons but none of the column headers or labels. This suggests a highly organized, complex economy, a civilization that managed its resources with meticulous precision. What sophisticated mathematical or logistical concepts might these records contain? Were they tracking astronomical cycles for agricultural planning or managing intricate trade networks that spanned the Mediterranean? The potential insights into ancient economics and statecraft are immense, yet they remain just out of reach. The linguistic isolation of these scripts is a central part of the puzzle. Over the centuries, scholars have tried to link linear to every known language family under the sun, from Semitic languages to Anatolian Luwian, but no proposed decipherment has gained widespread acceptance. The prevailing theory is that linear represents the language of the original Minoan inhabitants, which appears to be a linguistic isolate, unrelated to any other known tongue. This is what makes the code so difficult to crack. With the Rosetta Stone, scholars had a known language, ancient Greek, to use as a key to unlock the Egyptian hieroglyphs. For Linear A, we have no such key. The later Mycenaean Greeks adapted the script to write their own language, creating Linear B, which was successfully deciphered in the 1950s. While this gives us the sound values of the symbols, since we can read Linear B, applying those same sounds to Linear A just produces gibberish, because the underlying language is completely different. It's like trying to read a Spanish text using Italian pronunciation rules. Some things might seem familiar, but the meaning is utterly lost. This loss is profoundly consequential because the Minoans were the cultural precursors to the later classical Greeks. Their influence is undeniable, from mythological threads like the legend of the Minotaur and the labyrinth to architectural and artistic techniques. What crucial knowledge did they pass on that was lost when their palaces were destroyed, likely by a combination of natural disasters and invasion, around 1450 BCE? Their tablets could hold the missing manual for their incredible architectural acoustics or their advanced water management systems. They might contain detailed rituals that explain the central role of the bull in their culture or the purpose of the mysterious ceremonial axes found in caves. Perhaps most intriguingly, they could hold observations of the Thera eruption, one of the largest volcanic events in human history, which devastated their satellite island of Santorini and likely contributed to their decline. A first-hand account of that cataclysm would be an archaeological treasure beyond measure. The silence of these scripts is a powerful reminder that history is not just written by the winners, but also by those who leave behind a language we can understand. The Minoans were a dominant maritime power for centuries, a thriving, vibrant, and incredibly innovative culture, and yet their own words are silent. Every undeciphered symbol on a linear tablet is a door we cannot yet open, a conversation we are unable to join. The potential hidden within these texts is limitless. They could confirm our theories about Minoan society, or they could completely shatter them, revealing a people with an understanding of the world that we have not even begun to suspect. Until the code is broken, the full story of this foundational European civilization and the true extent of its technological and scientific wisdom remains one of history's most captivating and unresolved secrets. While the Minoans' linguistic secrets remain locked in clay, another ancient civilization guarded a different kind of knowledge, one forged in fire and wielded on the battlefield. Far from the Mediterranean coast, in the rugged highlands of ancient Anatolia, the Hittites achieved a metallurgical breakthrough that would redefine power in the Bronze Age world. Around 1500 years before the Common Era, while most armies were armed with bronze, Hittite smiths learned to master a far more formidable material, iron. This wasn't the weak, spongy iron of earlier, primitive attempts. Through a secret and highly controlled process, they were creating weapons of steel, a technological leap that gave them a terrifying advantage over their rivals. Imagine facing a Hittite army where your bronze sword could chip or bend against the superior strength of their iron blades, a disparity in technology that must have seemed almost supernatural to those who encountered it. Their mastery was not a simple matter of finding iron ore and heating it up. The Hittites developed a sophisticated understanding of the entire smelting process, a series of steps that required precision and control far beyond simple blacksmithing. It began with the selection of specific iron ores, likely magnetite or hematite, which they would crush and mix with charcoal. The real magic happened inside their specially designed furnaces, which were more than just pits for a fire. These were clay or stone structures, often built on slopes to take advantage of natural air drafts, though they may have also used bellows to achieve the critically high temperatures needed. The goal was to create a reducing atmosphere, a chemical environment that would strip the oxygen from the iron ore, leaving behind a mass of metallic iron mixed with slag, known as a bloom. But the Hittites went much further. They understood that the secret to transforming this brittle iron into something stronger lay in the careful management of carbon. This process of carbon infusion, known as carburization, is what set them apart. By maintaining a specific temperature range hot enough to allow carbon atoms from the charcoal to migrate into the solid iron, but not so hot that the metal melted, they were effectively creating steel. The consistency with which they achieved this is what continues to baffle historians and metallurgists. Without thermocouples or pyrometers, how did they so reliably judge the temperature within their furnaces? It's likely they became expert readers of the fire's color and the behavior of the materials inside, knowledge gained through generations of painstaking trial and error, closely guarded within guilds of smiths who served the royal court. The resulting steel was then worked meticulously, hammered while hot to fold and weld the metal, squeezing out impurities and distributing the carbon evenly to create a weapon that was both hard enough to hold a sharp edge and flexible enough to withstand the shock of combat. The military edge this provided cannot be overstated. In an era dominated by bronze, a material that required scarce tin to produce, the Hittites had tapped into a resource that was far more common. Iron ore was widespread across Anatolia, meaning they could equip larger armies without relying on vulnerable trade routes for tin. Their iron weapons were not just more common, they were objectively better. A well-made steel blade could slash through a bronze helmet, and an iron spear point could penetrate bronze armor that would easily turn aside a bronze weapon. This technological supremacy became a cornerstone of their empire, a state secret so valuable that the Hittite kings went to great lengths to control the knowledge and the output. Cuneiform tablets from their capital of Hattusa speak of kings gifting iron objects to foreign dignitaries as lavish presents, highlighting its status as a precious metal, more valuable than gold or silver because of its power to secure victory. And then it was gone. The collapse of the Hittite Empire around 1200 years before the Common Era, likely due to a combination of invasion, internal strife, and widespread drought and famine, led to a catastrophic rupture. The centralized state that protected and employed the master smiths disintegrated. The complex knowledge passed down through apprenticeships and tightly controlled by the state, fragmented and dissipated. The regions descended into a dark age, and the sophisticated art of quality iron smelting was lost for centuries. What followed was a long period of regression, where ironworking became crude and unpredictable. The weapons of the subsequent era were often inferior to the old bronze ones. They were softer, more brittle, and unreliable. It would take nearly 400 years for the techniques of consistent steel production to be slowly and independently rediscovered, marking the true beginning of the Iron Age. This loss is a stark lesson in the fragility of technological progress. The Hittite achievement wasn't just forgotten. It was completely erased from the cultural memory of the region for generations. Modern scientists are now using advanced methods like metallographic analysis on surviving Hittite artifacts, studying the microscopic structure of the metal to reverse engineer their recipes and furnace atmospheres. Each discovery reveals a deeper level of sophistication. Their legacy is a powerful reminder that technological dominance is not a permanent state. It is a candle flame that can be extinguished by the winds of upheaval, leaving future civilizations to stumble in the dark, slowly relearning what was once known, wondering at the silent, rust-streaked evidence of a greatness that was allowed to vanish. Standing silently in a courtyard in Delhi, a testament to ancient metallurgical genius defies one of nature's most relentless forces, corrosion. The Iron Pillar of Delhi, erected around 400 CE, is not merely an old artifact, it is a scientific conundrum cast in iron. Rising 23 feet into the air and weighing over 6 tons, it has endured over 1,600 years of monsoon rains, scorching heat, and humid air without succumbing to the red, flaking decay that claims modern iron structures within decades. This isn't a result of a dry climate or sheer luck. It is the product of a sophisticated, deliberate, and lost understanding of materials. The pillar's pristine surface, still smooth to the touch after centuries, is protected by a thin, invisible, and remarkably stable layer that has effectively made it rust-proof, a feat that our advanced science can observe and admire but has never been able to perfectly duplicate. The secret lies not in a magical coating, but in the very recipe of the metal itself. Modern spectroscopic analysis has revealed that the ancient Indian ironsmiths, known as lohars, created a composition that was both pure and ingeniously imbalanced by today's standards. While our modern steel prioritizes low phosphorus content to prevent brittleness, the Delhi pillar's iron contains a surprisingly high amount of phosphorus, about 1%, and a relatively low amount of manganese and sulfur. This precise, if counterintuitive, formula is the key to its longevity. When the pillar was forged, likely by hammer welding individual lumps of hot iron into a single massive column, the high phosphorus content facilitated the formation of a protective passive layer. This shield, only a few hundred microns thick, is a complex mix of iron, oxygen, hydrogen, and phosphates. It forms a robust, adherent barrier that prevents oxygen and moisture from reaching the underlying metal, effectively halting the electrochemical reaction we know as rust. It's a perfect example of ancient materials science, achieving through empirical mastery what we would now call corrosion engineering. The true marvel and the core of the mystery is the forging process itself. How did these artisans, working with small furnaces and hand bellows, achieve such a uniform and pure iron bloom? They used a method called the solid-state reduction technique, where iron ore was mixed with charcoal and heated in a clay furnace. The carbon from the charcoal acted as a reducing agent, pulling the oxygen out of the ore to leave behind a spongy mass of metallic iron called a bloom. This bloom was then repeatedly heated and hammered to squeeze out the molten slag impurities, a process that required an incredible eye for the quality of the metal. The skill was in knowing exactly how long to heat, how hard to hammer, and how to judge the metal's composition by its color and behavior in the fire. This wasn't mass production. It was a high art form, a knowledge passed down through generations of smiths who could literally feel the quality of the iron they were creating. This hands-on, tacit knowledge was never written down in a manual, and it is this intimate, tactile understanding of the process that our modern automated factories, for all their precision, cannot replicate. We can analyze the product with electron microscopes, but we have lost the artisan's touch that created it. The pillar's inscription, written in elegant Sanskrit, adds another layer of intrigue. It proclaims that the pillar was erected to honor a powerful king named Chandra, likely Chandragupta II of the Gupta Empire, and that it was originally located at a place called Vishnupada, often associated with the ancient center of Udayagiri. It speaks of a king who conquered his enemies and whose glory was as vast as the earth, but it says nothing of the pillar's most astonishing feature, its resistance to time. The builders saw its incredible durability not as a scientific marvel to be explained, but perhaps as a given, an expected outcome of their superior craft. This forces a profound question. Was the Delhi pillar a unique masterpiece, or was it simply one surviving example of a widespread technological capability? What other structures, tools, or artworks were created with this same knowledge that have since been lost to looters, recycling, or simply the ravages of time? The existence of other large iron objects from the same period, though none as famous or as large as the Delhi pillar, suggests this was part of a broader tradition of advanced ironworking on the Indian subcontinent. This leads to a fascinating possibility that ancient India possessed an entire suite of anti-corrosion technologies now lost to history. Historical texts like the Arthashastra describe processes for preventing the rusting of weapons in royal armories, mentioning treatments involving specific oils and powders. Were these treatments purely superficial, or did they work on a similar chemical principle to alter the surface of the metal? Could there have been other alloying techniques, perhaps using different local ores or organic materials, that created similarly durable objects for everyday use? The pillar stands as a silent, towering clue pointing toward a much deeper and more sophisticated material science culture than our history books currently reflect. It challenges our modern assumption that corrosion resistance is a relatively recent scientific breakthrough, suggesting instead that ancient innovators had found elegant, sustainable solutions to problems we are still grappling with today. In an age concerned with sustainability and building things to last, the Iron Pillar of Delhi is more than a historical curiosity. It is a benchmark, a challenge from the past urging us to look beyond our current methods and rediscover the lost art of creating things that truly endure. Yet for all the strength of iron and the resilience of stone, no civilization can thrive without its most precious resource, water. In the searing heat of the Persian plateau, where rainfall was scarce and surface water evaporated under a relentless sun, ancient engineers confronted this fundamental challenge with a solution of breathtaking elegance and ambition. They looked not to the sky but deep beneath the earth, pioneering a subterranean water network that would transform barren deserts into flourishing oases. These were the qanats, a system of underground aqueducts whose invention over 3,000 years ago represents one of history's most enduring and sustainable feats of hydraulic engineering. Unlike the towering aqueducts of Rome that marched across the landscape, the qanats worked in secret, a hidden lattice of tunnels that silently delivered life-giving water across vast distances without a single drop lost to evaporation. The principle was simple in concept but staggeringly complex in execution. It began with identifying a water source, typically an aquifer at the foot of a mountain range where groundwater collected from melting snow. From there, skilled surveyors, known as muqanis, would plot a gently sloping tunnel from the water source all the way to the destination village or farmland, often many miles away. The slope was the heart of the entire system. It had to be precise enough for gravity to pull the water steadily forward, yet gradual enough to prevent the tunnel from eroding and collapsing. Without lasers, levels, or GPS, how did they achieve this perfect grade, sometimes as little as 1 meter of drop per kilometer of tunnel? They used nothing more than sighting poles and perhaps a simple water level, relying on generations of accumulated knowledge and an intuitive grasp of the landscape. The tunnel itself would be dug from the destination point backward toward the source, with a series of vertical shafts sunk every 20 to 35 meters along the route. These shafts served dual purposes. They provided ventilation for the diggers and, crucially, allowed for the precise removal of excavated material, essentially creating a dotted line of access points across the desert surface that masked the continuous tunnel snaking below. The construction was a dangerous and highly specialized craft passed down through family lineages. Teams of muqanis would descend into these deep, narrow shafts to dig the horizontal tunnel, working in cramped, dark, and oxygen-poor conditions. They used hand tools to chip away at the rock and soil, and the excavated material was hauled up in leather buckets by teams at the surface. The risk of tunnel collapse was constant, and the work required an intimate understanding of different soil types and how to support them with reinforced rings. The knowledge required was immense, not just of engineering, but of geology and hydrology. A master muqani could read the soil, knowing exactly where to find water and how to navigate through unstable ground. This was a technology built on deep, localized, tacit knowledge, a wisdom of the hands and the earth that was rarely written down. The loss of this detailed construction technique in many regions is a classic example of how such artisan knowledge can vanish when it is no longer practiced, leaving behind only the ghostly lines of vertical shafts dotting arid landscapes, marking the corpse of a dead qanat. The impact of this technology was nothing short of revolutionary. A single qanat could sustain an entire community, providing a reliable, clean water supply for drinking, bathing, irrigation, and even powering watermills. It allowed great cities like Persepolis to rise in the desert and enabled the Persian Empire to support a large population in an otherwise inhospitable environment. The system was incredibly democratic. The water was often distributed through a carefully managed time-share system, ensuring every farmer received a fair allotment. The effectiveness of the qanat was so profound that the technology spread along trade routes from China to North Africa and even to Spain, where they are known as Viajes de Agua. Remarkably, many of these ancient tunnels are still in use today, a testament to their flawless design. In modern Iran, thousands of qanats remain operational, and the city of Gonabad relies on a qanat system dating back over 2,500 years. This enduring success stands as a powerful critique of our modern water infrastructure. We pump aquifers dry with powerful electric pumps, build massive, evaporation-prone reservoirs, and transport water across continents in energy-intensive processes. The qanat, by contrast, is a model of sustainability. It taps aquifers gently without depleting them, delivers water without any external energy input, and does so with zero waste. Its very existence challenges our assumptions about progress, suggesting that ancient societies developed profoundly elegant solutions to environmental problems that we now tackle with brute force and high technology. The abandoned qanats crumbling across the Middle East are not just archaeological curiosities. They are forgotten manuals for living in harmony with a dry land. Their silent, underground flow carries a message from the past, urging us to look beyond powerful pumps and concrete canals, and to remember that sometimes the most advanced solution is not the most complex, but the one that works in perfect, quiet balance with the natural world. But if the qanats represent a mastery of harnessing water, the ancient Egyptians demonstrated an equally profound command over another fundamental element: fire, transforming sand into objects of breathtaking beauty and spiritual power. Long before glass became a common household material, Egyptian artisans were conducting what can only be described as alchemy, turning humble desert silica into a radiant, jewel-like substance. As early as 1,500 years before the Common Era, they weren't just making simple glass. They were creating a sophisticated medium for art, religion, and commerce, developing techniques and formulas so advanced that some of their colors still defy perfect replication today. Their primary method was a painstaking process known as core forming, a technique that required immense patience and skill. It began with shaping a core of clay and dung around a metal rod to form the rough interior shape of a vessel or amulet. This core was then repeatedly dipped into a crucible of molten glass, or the hot, viscous glass was trailed around it using a tool, building up the layers gradually. While the glass was still pliable, the artisan would roll it on a marble slab to smooth the surface and often drag tools through the layers to create intricate, swirling patterns of different colors. Once the object had cooled, the clay core was painstakingly scraped out, leaving behind a hollow, fragile masterpiece. This was how they created their famous perfume bottles, slender vases, and intricate amulets, each one a unique product of fire and human ingenuity. The entire process was a high-wire act of thermal management, knowing exactly how long to heat the glass to keep it workable without it becoming too runny or too stiff. The true magic, however, lay in their chemical prowess. The base glass itself was made from silica, essentially crushed quartz pebbles or sand, fluxed with soda from plant ashes or natron to lower its melting point, and stabilized with lime. But it was their use of metal oxides as colorants that reveals a deep, empirical understanding of material science. They discovered that adding cobalt produced a deep, rich blue, while copper could yield either a turquoise blue or a reddish opaque glass known as copper red, depending on the furnace atmosphere. Manganese gave them a royal purple, and antimony or lead was used to create an opaque white or yellow. Their most legendary achievement, however, was Egyptian blue, considered the first synthetic pigment in history. By precisely heating a mixture of silica, lime, copper, and an alkali like natron to around 850 degrees Celsius, they created calcium copper silicate, a stable, bright blue crystalline compound that could be ground into a powder for paint or used as a coloring agent in glass and faience. The consistency with which they achieved this specific chemical reaction, controlling temperature and ingredients without modern instruments, is a staggering feat. This knowledge was not merely technical, it was deeply symbolic and economically vital. Specific colors held powerful religious meanings. Blue echoed the life-giving waters of the Nile and the heavens of the gods, while green evoked fertility and rebirth. Glass inlays were used for the eyes of sacred statues, believed to grant them a lifelike presence, and intricate glass beads adorned the mummies of the elite to protect them in the afterlife. Beyond the temple and the tomb, glass became a valuable commodity. Egyptian glassware was highly prized across the Mediterranean and Near East, a luxury item traded for other precious goods, making the secrets of its production a closely guarded state secret. The artisans who possessed this knowledge were among the most valued in the kingdom, and their workshops were likely attached to royal palaces or major temple complexes, operating under the direct patronage and protection of the pharaoh. And then this brilliant flame was largely extinguished with the decline of the New Kingdom and the subsequent absorption of Egypt into the Roman Empire. The specialized, highly localized knowledge system that supported this advanced glassmaking began to fracture. The Roman industry favored different, more mass-producible techniques like glassblowing, and the specific recipes for colors like the iconic Egyptian blue fell out of use and were eventually forgotten. For centuries, this vibrant hue was absent from the artist's palette, its formula a complete mystery. It wasn't until the late 19th century that chemists analyzing ancient samples were able to identify its composition, and even today, reproducing its exact shade and crystalline structure using only period-appropriate materials remains a challenge for experimental archaeologists. The story of Egyptian glassmaking forces us to expand our definition of ancient chemistry. It wasn't conducted in laboratories with beakers and formulas, but in smoky, hot workshops through generations of trial and error, observation, and handed-down technique. These artisans were, in effect, applied chemists who understood the properties of metal oxides and the effects of temperature and atmosphere on their reactions. The loss of their specific recipes is a poignant reminder that technological progress is not always a straight line. A craft can reach a dazzling peak of sophistication and then, due to political upheaval, economic shift, or simply a change in fashion, can be abandoned and its deepest secrets lost for a millennium. The surviving fragments of Egyptian glass, glowing with their undimmed brilliance, are more than just beautiful artifacts. They are tiny, luminous windows into a forgotten world of science and art, where the transformation of sand into jeweled light was considered not just a craft, but a form of magic. While the Egyptians were mastering the alchemy of glass and the Persians were tapping hidden aquifers on the other side of the world, in the humid lowlands of ancient Mexico, another civilization was experimenting with the very essence of a plant to create a material that would define their culture. The Olmecs, often called Mesoamerica's mother culture, achieved a chemical breakthrough so profound that it would not be replicated in the modern world for over 3 millennia. As early as 1,600 years before the Common Era, they weren't just collecting the milky white sap or latex from the Castilla elastica tree, they were transforming it. Through a process of organic chemistry that we now call vulcanization, they turned a sticky, perishable substance into a durable, bouncy, and versatile material, rubber. The discovery of this process is a mystery that sparks the imagination. We can picture an Olmec artisan, perhaps by accident or through deliberate experimentation, combining the latex with the sap of a local vine, the juice from the roots of the morning glory plant. This wasn't a random choice. The morning glory juice contains sulfur-based compounds that are the key to the entire reaction. When these two natural ingredients were mixed together in the right proportions and then carefully heated over a fire, a remarkable transformation took place. The individual long-chain polymer molecules in the latex, which normally slide past each other, making the material soft and eventually brittle, began to form cross-links. These new bonds, bridged by the sulfur, created a three-dimensional network that made the material stronger, more elastic, and far more resistant to wear and degradation. It was a process of molecular reinforcement, a feat of material science conducted without a single written formula or modern laboratory. The applications of this technology were both profoundly practical and deeply spiritual. The most iconic use was for the massive rubber balls used in the Mesoamerican ball game, a ritual sport that was far more than mere entertainment. These solid balls, some weighing up to 8 pounds or more, were designed for a game that reenacted cosmic myths of death and rebirth, often played on a stone court that represented the world itself. The incredible bounce and durability of vulcanized rubber would have been essential for the fast-paced, often brutal game, where players used their hips to keep the ball in motion. But their innovation didn't stop there. Archaeological evidence shows the Olmecs used this stable rubber to create waterproof textiles, adhesive binders, and even hollow rubber figurines that may have been used in religious ceremonies. They had created the first synthetic polymer, a material that could be shaped and molded to suit a vast array of human needs. This stands in stark contrast to the modern history of rubber. For centuries after European contact, natural rubber remained a frustrating novelty in the West. It would melt in the summer heat, become brittle in the winter cold, and was largely unusable for any serious application. It wasn't until the 1830s that Charles Goodyear, after years of failed experiments, stumbled upon the process of adding sulfur and lead and applying heat, finally achieving stable vulcanization. He hailed it as a transformative discovery, which it certainly was for the Industrial Revolution. Yet the Olmecs had perfected their own version of this chemical process over 3,000 years earlier, a fact that forces a complete re-evaluation of our timeline of innovation. The loss of this knowledge is particularly poignant because it was likely not a single secret, but a whole spectrum of recipes. Different ratios of latex to morning glory juice, varying temperatures, and specific heating times would have produced rubbers with different properties, some softer for adhesives, some harder and bouncier for balls. This nuanced understanding was part of an oral tradition, a hands-on knowledge passed from master to apprentice. When the Olmec civilization declined around 400 years before the Common Era, their major ceremonial centers were abandoned, and this specialized technological knowledge fragmented and faded away. Later cultures like the Maya and Aztecs used rubber, but there is little evidence they possessed the same sophisticated vulcanization techniques. They often used pure, less stable latex. The Olmec rubber story is a powerful testament to the innovative human spirit operating within a natural world viewed as a vast chemical laboratory. They looked at a weeping tree and a climbing vine and saw not just plants but potential. They understood their environment on an intimate molecular level, recognizing the hidden properties within organic materials and how to unlock them through combination and heat. Their achievement shatters the stereotype of ancient peoples as primitive or technologically stagnant. Instead, it reveals them as brilliant applied scientists, whose discoveries in material science were so advanced that they would not be independently rediscovered until the dawn of the modern industrial age. The silent, rubbery artifacts they left behind are not just curiosities. They are enduring proof that some of history's most revolutionary ideas were born not in steel factories, but in the heart of the jungle. Yet even as we ponder the grand hydraulic networks of the Persians and the material science of the Olmecs, we find a civilization whose mechanical imagination seemed to leap centuries ahead of its time, crafting wonders that feel almost anachronistic. In the bustling intellectual hub of Alexandria, under the patronage of the Ptolemies, engineers like Hero were not just building structures, they were building illusions, crafting machines that moved with a life of their own. This wasn't mere gadgetry, it was the birth of automation, a field that would lie dormant for over 1,000 years. Hero's creations, detailed in his manuscripts like Pneumatica and Automata, were powered by the fundamental forces of steam, water, and compressed air, principles we now recognize as the bedrock of mechanical engineering. He designed self-opening temple doors that would swing apart seemingly by divine will when a priest lit a fire on the altar, a clever trick using heated air to expand water and counterweights. He built singing mechanical birds that could be triggered to whistle by the force of water displacement, and he even created what is considered the world's first vending machine, a device that would dispense a measured amount of holy water when a coin was inserted, its weight temporarily tilting a lever. The sophistication of these devices points to a profound understanding of the physical world that was utterly lost. Hero and his contemporaries grasped the power of steam, constructing an ingenious device called an eolipile, essentially a primitive steam engine where a spinning sphere was propelled by jets of steam. While it was treated as a fascinating novelty, a temple wonder, the underlying principle was the very same that would later drive the Industrial Revolution. The potential was there, shimmering in the Alexandria sunlight, but it remained untapped. This loss is perhaps one of the most poignant what-ifs in the history of technology. Imagine if this knowledge had been developed further, if the eolipile had been scaled and applied to practical tasks like pumping water or powering machinery. The course of human history might have accelerated dramatically. The decline of the Hellenistic world and the eventual fall of the Roman Empire caused this vibrant thread of mechanical innovation to snap. The intricate knowledge required to craft these automata, preserved in scrolls and through master-apprentice relationships, fragmented and faded away. The devices themselves, likely built from perishable materials like wood and bronze, crumbled into dust. For over a millennium, the complex principles of pneumatics and mechanics that Hero had so brilliantly demonstrated were forgotten, only to be painstakingly rediscovered during the Renaissance and later the Enlightenment. This gap of 1,500 years represents a colossal delay in our technological evolution, a stark reminder that progress is not inevitable and that brilliant ideas can be extinguished by the tides of history. Hero's work completely reframes our view of the ancient world. We are accustomed to venerating the Greeks for their philosophy, their art, and their democracy, but we must now also see them as preeminent engineers and proto-scientists. Their workshops were laboratories, their temples were stages for technological theater. The loss of their mechanical wonders forces us to ask a haunting question. How many other inventors like Hero existed whose works were lost entirely? Were there other treatises that burned in the Library of Alexandria that detailed even more advanced concepts? The surviving fragments of Hero's legacy are not just curiosities. They are proof that the spark of invention, the drive to automate and mechanize, is not a modern phenomenon. It is a deeply human impulse, one that flourished in antiquity with a brilliance that would not be seen again for centuries, a ghost in the machine of history waiting to be rediscovered. While Hero's automatons represented a playful and public-facing application of engineering genius, another ancient civilization focused its innovative spirit on a far more pragmatic and formidable goal, achieving absolute mastery of the seas. The Carthaginians, the great mercantile and martial rivals of Rome, understood that their power and prosperity depended entirely on their ability to control the Mediterranean. To secure this dominance, they engineered not just ships, but the very ports that housed them, creating naval bases of such sophistication and strategic brilliance that they remain marvels of ancient military architecture. At the heart of their capital city lay not one but two interconnected harbors, a testament to their dual identity as masters of commerce and war. The commercial harbor was impressive enough, a vast rectangular port that welcomed traders from across the known world. But it was the military harbor, the Kothon, that truly showcased their unparalleled engineering prowess and their deep understanding of naval power. This military harbor was a breathtaking feat of design, a perfectly circular artificial basin carved out of the coastline, reminiscent of a massive inland donut. Encircling the central lagoon was a continuous, ring-shaped island, and lining the outer edge of this island and the inner wall of the harbor itself were hundreds of individual, covered slipways, essentially garages for warships. Each of these vaulted dry docks was designed to shelter a single vessel, protecting its hull from the destructive marine worms that could devour wooden ships and keeping its crew and rigging safe from the elements. This design offered a staggering strategic advantage. In an era when most navies had to haul their ships onto open beaches, leaving them exposed to weather and surprise attack, the Carthaginian fleet was always battle-ready, housed in a fortified, weatherproof complex. The entire harbor was encircled by a massive high wall, preventing any outsider from seeing the number of ships, their state of readiness, or any secret preparations underway. The true stroke of genius, however, lay in the hidden mechanics of this naval fortress. The entrance to this circular harbor was not a simple, open channel. It was a cleverly concealed and likely gated passageway that connected it to the larger commercial port. This meant the entire Carthaginian navy could be launched from its protected berths, through the commercial harbor, and out to sea in a rapid, organized, and shocking deployment. Historical sources suggest this complex hydraulic system may have included sluice gates or other mechanisms to control water flow and siltation, keeping the harbors deep and navigable. The scale was immense. Estimates suggest the circular harbor could hold over 170 warships, each with a crew of over 100 men, meaning this single facility could mobilize an army of 17,000 highly trained sailors at a moment's notice. It was a machine for war, a perfectly engineered ecosystem designed for one purpose: to project overwhelming naval power. This technological edge was a cornerstone of Carthage's empire, allowing them to dominate trade routes and defend their interests for centuries. Their shipwrights were also innovators, likely developing advanced construction techniques to build their famous quinqueremes massive oared warships with speed and efficiency. The entire operation, from the drafting of the harbor's precise circular geometry to the management of its water levels, speaks to a society with a profound grasp of engineering, logistics, and hydrodynamics. They didn't just build with stone, they sculpted the coastline itself to serve their strategic needs, turning their capital into an impregnable fortress for their fleet. And then it was all systematically erased. The utter destruction of Carthage by Rome at the end of the Third Punic War in 146 BCE was so complete that it has become a byword for annihilation. The city was razed, its fields salted, and its population killed or enslaved. With the city died its secrets, the intricate knowledge of how to design and maintain such a complex harbor system, the architectural plans, the engineering principles for managing water flow and preventing siltation. The very concept of a centralized, protected naval dockyard was lost. The Romans, brilliant engineers in their own right, never built anything quite like it. Their naval bases were typically more open and functional, lacking the layered defensive and logistical genius of the Carthon. It would be well over 1,000 years before similar dedicated, fortified naval harbors would appear again in Europe. The loss of Carthaginian harbor engineering is a stark lesson in how victory can sometimes incinerate knowledge. In their fervor to eliminate a rival, the Romans ensured that a unique and brilliant school of marine architecture was extinguished forever. We are left to piece together its wonders from scattered historical accounts and the faint outlines that remain visible at the archaeological site in modern-day Tunis. These ghostly traces in the earth hint at a circular perfection, a geometric ambition that speaks of a civilization thinking on a grand strategic scale. The Carthon stands as a silent monument not just to Carthaginian ingenuity, but to the tragic fragility of specialized knowledge, a reminder that some of history's most brilliant innovations can be washed away by the tides of war, leaving behind little more than a haunting and enigmatic footprint in the sand. Imagine a world without GPS, without magnetic compasses, where finding your way across vast, featureless landscapes was a matter of life and death. Now picture a solution so ingenious it seems to defy its own era. A wooden chariot, adorned with an ornate figure that perpetually points its outstretched arm toward the south, no matter how many turns the carriage makes. This was the south-pointing chariot, a legendary device from ancient China that first appears in historical records around the 3rd century of the Common Era. It wasn't guided by any mystical force or hidden magnet. Its unwavering sense of direction was a product of pure, unadulterated mechanical genius, a system of interlocking gears so sophisticated that it stands as one of history's most fascinating early forays into what we would now call robotics. The core of its magic lay in a principle known as differential gearing, a concept that wouldn't become commonplace in the West until the 19th century, when it was applied in modern automobiles. Here's how it likely worked. The chariot's movement was transmitted from its 2 wheels through an intricate assembly of gears. The key was that the 2 wheels were not connected to the central figure on top by a single, simple axle. Instead, the system was designed to account for the difference in rotation between the wheels. When the chariot moved in a straight line, both wheels turned at the same rate, and the gears moved in unison, keeping the pointer stable. But when the chariot turned, say, to the right, the left wheel would have to travel a greater distance than the right wheel. This difference in rotation would be calculated by the gear train, causing the central mechanism to rotate the figure to the left at a precise rate, exactly counteracting the turn of the chariot and keeping it pointing south. It was a closed-loop mechanical system, a physical algorithm designed to solve a complex navigational problem in real time. The implications of this are staggering. The ancient Chinese engineers who designed this device possessed a profound understanding of rotational mechanics and mathematical ratios. They had to calculate the exact gear ratios needed to translate the differential motion of the wheels into the correct compensatory movement of the pointer. This required an advanced knowledge of precision manufacturing to craft wooden gears that meshed perfectly without slipping or jamming. They were, in effect, building an analog computer made of wood and lacquer, a machine that could perform calculations about its own movement and adjust its output accordingly. This places the south-pointing chariot in a category far beyond a simple tool. It was an automaton, a thinking machine in the most literal sense, showcasing a level of mechanical abstraction that we simply don't associate with the ancient world. And yet, for all its legendary status, the south-pointing chariot is a ghost. No original examples have survived the ravages of time. Our entire understanding of it comes from textual descriptions in ancient Chinese texts, which provide tantalizing clues but lack the detailed engineering diagrams we would need for a perfect reconstruction. This absence is the heart of the mystery. How did these master engineers design such a complex device without detailed blueprints or computer-aided design? The answer almost certainly lies in a tradition of hands-on knowledge and master-apprentice relationships that has been completely lost. The design was likely conceptualized, refined, and built through physical models and a deep, intuitive understanding of mechanics, a form of knowledge that was transmitted through practice and demonstration rather than written manuals. The loss of this tactile engineering culture means that modern attempts to recreate the chariot are exercises in historical detective work, with each successful model bringing us closer to understanding the brilliant minds that conceived it. The purpose of the chariot adds another layer to its significance. While it may have had practical applications for navigation, especially in dusty conditions or fog where landmarks were obscured, it was likely far more important as a symbol of imperial power and technological superiority. For a Chinese emperor, possessing such a wondrous device was a potent symbol of his mandate from heaven, a demonstration that his court could harness the very laws of the universe. It was a masterpiece of political theater, a testament to a civilization that valued intellectual achievement and mechanical innovation as pillars of its identity. The south-pointing chariot forces us to completely reimagine the technological landscape of the ancient world. It wasn't a place of simple levers and pulleys. It was a place where differential gears whirred silently in wooden cases, where automata performed seemingly magical feats, and where the line between machine and magic was beautifully, brilliantly blurred. While the Carthaginians sculpted their coastline into a fortress and the Chinese built mechanical marvels of navigation, a different kind of engineering brilliance was flourishing indoors, focused not on conquest or guidance, but on the fundamental comfort and health of daily life. On the sun-drenched island of Crete, the Minoan civilization was achieving a level of urban sanitation that would not become standard in many parts of the world for another 3,500 years. At the heart of this achievement was the magnificent palace of Knossos, a complex so advanced that it boasted a plumbing and drainage system of breathtaking sophistication, all built around 2,000 years before the Common Era. This was not a crude or rudimentary setup. It was a carefully engineered network that provided fresh water, removed waste, and offered amenities that would be considered the height of luxury for centuries to come. The system began with the meticulous management of water supply. The Minoans mastered the art of capturing water from springs and mountain streams, channeling it through a series of terracotta pipes that were expertly designed to maintain a consistent flow. These pipes were not simple cylinders. They were ingeniously tapered, with a narrower end that fit snugly into the wider end of the next section. This design did more than just create a watertight seal. It actually increased the water pressure as it moved through the system, preventing sediment from settling and ensuring a powerful, clean flow throughout the vast palace complex. The pipes were then carefully buried underground or set within walls, protected from damage and from the heat of the Mediterranean sun, keeping the water inside surprisingly cool and fresh. Once inside the palace, this water was put to use in ways that seem almost modern. Archaeological evidence reveals rooms equipped with terracotta tubs that functioned as showers, with drainage holes in the floor to carry away the wastewater. But the most astonishing feature by far was the flush toilet. Several rooms in Knossos contained stone seats with a familiar, keyhole-shaped design, connected to a hidden drainage channel below. A conduit from a nearby water source would have allowed a user to pour water down the channel to flush waste away, sending it on a journey through the palace's intricate underground drainage system. This wasn't a luxury reserved for the king alone. Evidence suggests these facilities were available to many residents of the palace, indicating a societal-wide value placed on hygiene and privacy. The true engineering marvel, however, lay in the management of what happened next. The wastewater from these toilets, showers, and roof runoff didn't just dump into a pit. It was channeled through a comprehensive network of stone and terracotta drains that ran beneath the palace floors. The Minoan engineers had a masterful understanding of gravity and gradient, carefully calculating the slope of these underground channels to ensure a continuous, self-cleaning flow that prevented blockages and stagnant pools. These drains were large enough for a person to crawl through for maintenance, showing they were built to last and to be serviced. The entire system ultimately directed wastewater away from the living quarters and out of the palace, safeguarding the health of the inhabitants. The public health benefits of this technology cannot be overstated. In an era when many contemporary cities were plagued by waterborne diseases from contaminated wells and open sewers, the Minoans enjoyed a remarkable level of sanitation. By swiftly removing human waste and wastewater from their living environment, they drastically reduced the risk of cholera, dysentery, and typhoid. This advanced urban planning would have contributed directly to a healthier, more productive population, and it may well have been a key factor in the overall prosperity and longevity of Minoan society. Their civilization thrived for centuries, and this commitment to public health through engineering was undoubtedly a cornerstone of that success. This makes the complete loss of such a vital technology all the more tragic. When the Minoan palaces were destroyed around 1450 BCE, likely by a combination of the catastrophic Thera eruption and subsequent invasion, this specialized knowledge of hydraulic engineering was lost with them. The later Mycenaean Greeks who occupied the site did not maintain or replicate the system to the same degree of sophistication, while the Romans would later develop their own famed aqueducts and sewers. Their approach was different, focused on grand public works on a massive scale rather than the integrated personal sanitation solutions found in every corner of Knossos. In many ways, the Minoan system was more akin to modern indoor plumbing in its conception and accessibility. The silent, empty channels beneath the ruins of Knossos are more than just archaeological curiosities. They are a powerful challenge to our perception of historical progress. They force us to ask a difficult question: how much advanced knowledge focused on improving the quality of human life has been wiped out by disaster and forgotten by time? The Minoans remind us that ancient societies were not simply primitive precursors to our own. They were innovative cultures capable of creating solutions that were both brilliantly practical and profoundly humane. Their legacy is a haunting echo of a path not taken, a reminder that the comforts we consider modern might be ancient ideas waiting silently in the earth for us to rediscover them. High in the thin air of the Andes, where steep slopes and harsh climates would seem to defy agriculture, the Incas and their predecessors performed a miracle of landscape engineering. They didn't just farm the land, they sculpted it, transforming entire mountainsides into a breathtaking cascade of stair steps that reached for the sky. This was Andean terrace farming, or Andines, a technology so harmoniously integrated with its environment that it continues to function flawlessly centuries after the fall of the empire that perfected it. Each stone wall, each carefully graded step, and each hidden water channel represents a profound understanding of geology, hydrology, and microclimates, a lost science of sustainability that modern agriculture is only now beginning to fully appreciate. The construction of a single terrace was a masterclass in layered engineering, far more complex than simply piling rocks to hold back soil. It began with the foundation. Workers would first lay a base course of large stones to provide drainage and stability, preventing water from pooling and undermining the structure. On top of this, they placed a layer of smaller gravel and sand, which acted as a filter and a capillary barrier, stopping the finer soil above from washing down while still allowing excess water to percolate through. Only then would they add the deep, rich topsoil, often carried up from fertile valleys below. This carefully engineered profile created the perfect growing medium, well-drained, aerated, and resistant to landslides. The retaining walls themselves were built in the same ingenious style as their temples, using precisely cut, interlocking polygonal stones that could shift and settle during earthquakes without collapsing. This wasn't just farming, it was seismic-resistant civil engineering applied to agriculture, but the true genius of the system lay in its hydraulic heart. The terraces were useless without water, and the Inca engineers were masters of its capture and distribution. They built canals and aqueducts that stretched for miles, diverting water from high-altitude lakes and glaciers. The water was then channeled through the terraces in a controlled cascade. The design ensured that every level received its share, with small breaches or stone conduits allowing water to flow from one terrace to the next. This prevented erosion and guaranteed that even during dry periods, the lower terraces would benefit from whatever moisture seeped down through the soil from above. In some sophisticated systems, they even engineered subtle temperature gradients. Terraces built in a concave shape could capture and retain more solar heat, creating microclimates that were several degrees warmer than the surrounding air, allowing them to grow a wider variety of crops at altitudes that would otherwise be barren. This technological marvel enabled the Inca Empire to become a powerhouse of agricultural biodiversity. On these terraces, they cultivated over 3,000 varieties of potato, each breed meticulously selected for its resistance to frost, its yield in specific soil types, or its storage qualities. They grew quinoa, a complete protein that thrived in the high altitude, along with maize, oca, and mashua. This wasn't monoculture. It was a sprawling, open-air laboratory of genetic diversity and crop rotation, a system designed for long-term resilience rather than short-term maximum yield. The terraces allowed them to support a vast population in a geographically challenging environment, turning the mountains that could have been their greatest weakness into their most productive asset. The most haunting question is not how they built them, but why we have lost so much of the knowledge behind their management. While many terraces still stand, the intricate social and scientific systems that maintain them have largely faded. The Incas did not use a written language. Their engineering knowledge was passed down through generations via oral tradition and hands-on apprenticeship. The mita system, a form of communal labor duty, organized the massive workforce needed to build and maintain these structures. With the collapse of the Inca social order following the Spanish conquest, this chain of knowledge was broken. The conquistadors were interested in gold and silver, not in the subtle science of sustainable potato farming. They disrupted the communal land management practices and introduced European crops and farming methods that were often ill-suited to the Andean environment, leading to erosion and the abandonment of many terraces. Yet, the story doesn't end there. In a powerful testament to the technology's inherent brilliance, many rural Quechua and Aymara communities in Peru and Bolivia have continued to maintain and farm their ancestral terraces, preserving this knowledge through sheer necessity and cultural pride. They are the living guardians of a lost science. Modern agronomists and archaeologists now work alongside these communities, not to teach them, but to learn from them. They are studying how the ancient practices of water management and soil conservation can be applied to combat modern problems like desertification and soil degradation. The terraces are being recognized not as relics, but as repositories of vital knowledge on how to farm steep slopes in a changing climate. This ancient technology offers a starkly beautiful lesson in resilience. The Incas looked at a vertical, earthquake-prone, and often arid landscape and saw not limitations but potential. They designed a system that worked with the mountain's natural forces rather than against them. Their terraces prevented the catastrophic erosion that plagues modern hillside farming. They created their own fertile soil, and they managed water with a frugal precision that puts many modern irrigation systems to shame. In an era of climate uncertainty, the silent stone stairways of the Andes stand as a timeless monument to a different kind of ingenuity, one that seeks not to dominate nature, but to collaborate with it, creating abundance that endures for centuries. While the Incas reshaped mountains to feed their empire, another civilization was engaged in an equally monumental project, not of earth and stone, but of pure information, meticulously mapping the vast and silent movements of the heavens. In the Fertile Crescent between the Tigris and Euphrates rivers, the Babylonians embarked on a scientific endeavor of breathtaking scale and patience. Starting around 1800 years before the Common Era and continuing for over a millennium, they became the ancient world's premier data scientists, their laboratory the night sky, their recording device the humble clay tablet. These weren't casual notes, they were systematic, daily logs of everything that moved in the celestial sphere: the positions of the planets, the phases of the moon, the appearance of comets, and the timing of eclipses. This relentless, multi-generational project of observation created the longest and most detailed dataset of the pre-telescopic era, a treasure trove of information that would become the bedrock of all Western astronomy. The true brilliance of the Babylonian astronomers, known as Tupshar Enuma Anu Enlil, or scribes of the celestial gods, was not just in their diligent record-keeping, but in what they did with the data. They weren't content to simply note events. They searched for patterns, for cycles they could use to predict the future. Their most stunning achievement was in predicting lunar eclipses. By analyzing centuries of records, they discovered the Saros cycle, a period of approximately 18 years, 11 days, and 8 hours, after which the Sun, Earth, and Moon returned to nearly the same relative geometry, and a similar pattern of eclipses repeats. This was a monumental leap from superstition to science. Instead of viewing an eclipse as a random omen of divine displeasure, they came to understand it as a predictable, cyclical phenomenon governed by mathematical law. They could warn the king that an eclipse was likely to occur in a certain month, allowing the court to perform the necessary rituals to appease the gods and maintain order, effectively turning fear into a manageable administrative event. This predictive power was built upon a unique mathematical foundation: their base 60 or sexagesimal numeral system. This might seem like an odd choice to us, but it was a stroke of genius. The number 60 is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This mathematical flexibility made complex calculations and fractions incredibly easy to work with, a huge advantage when dividing the circle into 360 degrees or calculating the precise timing of celestial events. They expressed fractions just as we do with time today. For instance, a value like 23 and 15/60 was as simple for them as writing 23/15 is for us. This elegant system allowed them to develop sophisticated arithmetical models, a kind of pre-geometrical algebra, to track the variable speeds of the planets. They could break a planet's path into pieces, calculating its position at different phases of its cycle with remarkable accuracy, all without a physical model of the solar system or any concept of gravitational forces. Yet, for all we understand about their methods, profound mysteries remain, largely due to the tragic loss of context. We have the clay tablets that contain the finished, polished results of their calculations, the neat tables of planetary positions and eclipse predictions. What we are missing are the equivalent of their lab notebooks, the texts that would have explained the underlying reasoning, the theoretical leaps, and the thought processes that led them to these discoveries. How did they first stumble upon the Saros cycle? What debates occurred among the scholars in the temple libraries of Babylon or Uruk? Their texts are often frustratingly procedural, stating, "Do this, then this, to get this result," without explaining the why. This has led to a fascinating divide among modern historians of science. Were the Babylonians brilliant technocrats, unparalleled in their computational techniques, but lacking an overarching physical theory for the cosmos? Or did they possess a deeper, more conceptual understanding that was simply never written down in the surviving practical tablets? The legacy of this lost knowledge is immense. Their meticulously compiled data and computational techniques were passed east to India and west to Greece. Greek astronomers like Hipparchus and later Ptolemy directly built upon the Babylonian records, adopting their parameters for lunar and planetary motions. In many ways, the Almagest, Ptolemy's great work that dominated astronomical thought for 1400 years, is the culmination and synthesis of Greek geometrical models with Babylonian numerical data. This transmission of knowledge is a powerful reminder that scientific progress is rarely a series of isolated breakthroughs, but more often a slow, collaborative accumulation of understanding across cultures and centuries. The Babylonians provided the raw observational fuel that powered the engines of later astronomical revolutions. Their story is a testament to the incredible power of patience, precision, and the unwavering belief that the chaotic beauty of the night sky could, in fact, be understood through the quiet, persistent application of numbers etched into wet clay. Yet even as we marvel at the Babylonians' celestial computations and the Incas' agricultural terracing, we find another ancient innovation that literally laid the groundwork for modern civilization, an infrastructure so robust its bones still shape the landscapes of Europe and beyond. The Roman road network was far more than a series of paths. It was the physical circulatory system of an empire, a breathtaking feat of logistics, civil engineering, and long-term planning that has arguably never been surpassed. Stretching over 250,000 miles across 3 continents, from the rainy highlands of Scotland to the arid deserts of Mesopotamia, these roads were built not merely to last but to defy time itself. And defy it they have millennia later. Many of these ancient thoroughfares not only survive but still serve as the foundation for modern highways, their original stonework buried just beneath the asphalt of contemporary travel. This endurance is no accident. It is the direct result of a construction philosophy that valued permanence over convenience, a methodology so sound that modern engineers study it with a sense of awe. The genius of a Roman road was hidden in its cross-section, a meticulously crafted layered cake of materials that transformed unstable ground into an unyielding platform. The process began with the fossae, or trenches, dug several feet deep. Into this trench, the Romans would place the statumen, a foundation layer of large, flat stones that provided drainage and stability, preventing the road from sinking into the subsoil. On top of this came the rudus, a thicker layer of rubble mixed with lime, which formed a solid, coarse concrete. Next was the nucleus, a finer mix of gravel, sand, and clay that was meticulously compacted. The final, visible surface was the summum dorsum, a wearing course of interlocking, tightly fitted polygonal blocks of hard basalt or flint, expertly cambered so that rainwater would run off into drainage ditches lining the sides. This multi-layered system distributed weight efficiently, allowed for proper drainage, and prevented frost damage and ruts, creating a surface that could withstand the relentless pounding of armies, trade caravans, and the elements for centuries. The creation of this vast network required logistical skills that are staggering to contemplate. Before a single stone was laid, teams of agrimensors, or surveyors, would plot the straightest possible course across the landscape using an instrument called a groma to sight lines and a chorobates, a precise wooden level, to ensure gentle, consistent gradients. They overcame natural obstacles with a relentless, practical brilliance, carving through hillsides, raising causeways across marshes, and bridging rivers with arches of stone that still stand today. The organization of labor was equally impressive. The work was carried out by Roman legion soldiers who were as much engineers as they were fighters. This provided a disciplined, skilled, and mobile workforce that could be deployed to any corner of the empire, turning the military into the greatest construction company the world had ever seen. The procurement and transport of materials on this scale was a monumental undertaking involving quarries, lime kilns, and a fleet of carts, all coordinated without the aid of modern communication. The profound loss that followed the empire's collapse was not merely the knowledge of how to build these roads, but the complex ecosystem that maintained them. The Roman state understood that construction was only half the battle, preservation was key. A dedicated bureaucracy was responsible for upkeep, funded by tolls and taxes. The recipes for the mortars and concrete used in the foundations were likely closely guarded state secrets, passed down through guilds of engineers. With the disintegration of centralized Roman authority, this maintenance system vanished. The knowledge of how to quarry the right stones, mix the perfect binding agent, and execute the precise layering technique fragmented and was eventually forgotten. Later generations simply lacked the organizational capacity, technical knowledge, and economic resources to build or repair roads to this standard. They became, in effect, inheritors of a technology they could no longer replicate, left to marvel at and reuse the indestructible work of their predecessors. The impact of these roads transcended their physical form. They were the superhighways of information, culture, and power. "All roads lead to Rome" was not just a proverb, it was a statement of geopolitical reality. This network allowed legions to march from one crisis point to another with unprecedented speed, enabling the rapid projection of imperial power that held the vast territory together. It fueled economic prosperity by drastically reducing the cost and time of moving goods, connecting the wheat fields of Egypt with the markets of Gaul. Ideas, religions, and innovations traveled along these stone ribbons, facilitating a cultural exchange that helped shape the Western world. The Roman road was more than just crushed stone and mortar. It was a catalyst for unity, a tangible symbol of Roman order imposed upon the chaotic natural world, and a legacy of engineered resilience that continues to guide us quite literally to this very day. While the Romans mastered the movement of armies and the Incas the movement of water, the ancient Egyptians performed a different kind of magic. They mastered the movement of ideas across millennia, capturing thought itself in a medium so durable it speaks to us as clearly today as it did 4,000 years ago. This was the alchemy of ink, a technology born not of grand monuments but of the quiet scribe's workshop, yet its impact was every bit as profound as any pyramid. The Egyptians didn't just invent a writing fluid, they engineered a time capsule for the human mind, developing carbon-based inks of such astonishing permanence that the texts they produced have survived in crisp, legible condition, defying the relentless decay that has consumed so much of the ancient world. Their success was no happy accident. It was the result of a sophisticated chemical understanding of materials and their interactions, a lost recipe for immortality penned in soot and gum. The foundation of their most common ink, known as mehanet to the Egyptians, was a deceptively simple trinity of ingredients: carbon, water, and a binding agent. The carbon, providing the deep, opaque black pigment, was typically sourced from lampblack, the fine soot collected from oil lamps or from charcoal. This was more than just dirt. It was pure, stable elemental carbon, a material famously resistant to fading, chemical change, and the ravages of light. This pigment was then meticulously mixed with water, but the true stroke of genius was the third component, a binding medium, usually gum arabic, which is a natural sap harvested from acacia trees. This gum was far more than just a glue. It acted as a dispersant, preventing the carbon particles from clumping together, and as an adhesive, fixing the pigment firmly to the porous papyrus surface. When a scribe dipped his reed brush into this mixture and applied it, the water would be quickly absorbed by the papyrus, leaving the gum to harden around the carbon particles, locking them permanently in place. This created a mark that was not merely sitting on the surface, but was physically and chemically bonded to the writing material itself. Yet for all its effectiveness, the simple black ink was only the beginning of their chromatic artistry. For religious texts and illuminated manuscripts, like the magnificent Book of the Dead, Egyptian scribes transformed their palettes into a radiant spectrum using vibrant, mineral-based inks. These were not organic dyes that would fade, they were powdered jewels. They ground malachite for a brilliant and enduring green, the color of new life and resurrection. They used red ochre, a iron oxide clay, for a powerful red that symbolized chaos and life-giving power. The most precious and iconic was arguably Egyptian blue, the first synthetic pigment in history, created by carefully heating a mixture of silica, lime, copper, and alkali to form calcium copper silicate, a crystalline compound that retained its dazzling lapis lazuli-like hue for eternity. Each color carried deep symbolic meaning, turning a funerary text into a magical, polychromatic gateway to the afterlife. The enduring mystery and the heart of the lost technology lies not in the ingredients list, which we can often deduce, but in the precise preparation methods. How exactly did they grind the materials to achieve such a consistent, ultra-fine powder without modern milling equipment? What were the exact ratios of gum to pigment to water that created the perfect viscosity, fluid enough to flow smoothly from a brush yet thick enough to not bleed uncontrollably into the papyrus fibers? Were there other, more subtle additives, a drop of vinegar as a preservative, or a specific type of water, that played a role in the ink's legendary stability? These were the tricks of the trade, the tacit knowledge passed down through generations of scribble apprentices in a hands-on oral tradition. This knowledge was so effective that it never needed to be written down in a manual. It was simply known, practiced, and perfected until it became second nature. The decline of this exquisite technology was a slow tragedy driven by cultural and economic shift, not by failure. As the Ptolemaic and Roman periods progressed, papyrus scrolls began to be superseded by the parchment codex, sheets of prepared animal skin bound together like a modern book. Parchment had a different surface texture and absorbency than papyrus, requiring a different kind of ink. Meanwhile, from the 8th century onwards, paper, introduced from China via the Islamic world, began its eventual dominance. The inks developed for these new media, particularly iron gall ink made from tannic acid and iron salts, were cheaper and easier to produce in large quantities, but they came with a hidden curse. While dark and effective initially, iron gall ink is famously acidic. Over centuries, it can eat through the very paper or parchment it is written on, causing documents to become brittle and illegible, a slow chemical suicide. The ancient Egyptian carbon ink, by contrast, is chemically inert and neutral. It does not attack its host. It simply sits unchanged, a faithful guardian of the words it forms. This loss represents more than just a change in office supplies. It represents the breaking of a chain of knowledge that preserved human thought for longer than any other medium in history. The humble jar of Egyptian ink, a fusion of art and science, was the vehicle for everything from administrative records and love poetry to mathematical treatises and religious spells. It safeguarded the wisdom of the ages, allowing us to hear the voices of architects, priests, and merchants across an unimaginable gulf of time. Its silent, enduring presence on papyrus is a powerful challenge to our own digital age, where we store our collective knowledge on magnetic platters and silicon chips, formats that may become unreadable within a mere decade. The Egyptian scribe, with his soot, his gum, and his water, achieved a form of information permanence that our most advanced technologies are still struggling to match. A timeless lesson in building things to last from a civilization that truly understood the weight of eternity. As we reflect on the incredible ingenuity of the ancient world, From the celestial computer of the Greeks to the self-healing concrete of Rome, a humbling pattern emerges. These were not isolated flashes of genius in a dark and primitive past. They were the products of sophisticated, organized societies with deep wells of knowledge that was often hard-won through generations of observation, experimentation, and meticulous craftsmanship. The loss of these technologies forces us to abandon the comfortable myth of linear progress, the idea that we are inherently smarter or more capable than those who came before us. Instead, we see a far more complex and fascinating story, one of brilliant peaks of achievement, devastating valleys of forgetting, and the fragile threads that connect human innovation across the centuries. This journey through 29 mysteries is more than a catalogue of curiosities. It is an invitation to radically reconsider our place in history. We are not the inevitable pinnacle of human potential. We are simply another chapter in a long, nonlinear narrative of discovery. The ancient master smith who forged a Damascus steel blade understood the nanostructure of his material through the language of fire and hammer, an artistry we still struggle to replicate with our electron microscopes. The Inca stonemason who shaped a 20-angled block did so with an intuitive grasp of geometry and seismic forces that our modern engineering software is only now beginning to model. Their expertise, born of a deep, symbiotic relationship with their environment and materials, represents a different kind of science, one that was holistic, sustainable, and often breathtakingly elegant. Perhaps the most urgent lesson these lost arts hold for us is one of sustainability and resilience. In an age defined by climate crisis and disposable culture, the ancient world offers powerful alternative models. The Qanat systems of Persia delivered water across deserts for millennia without a single watt of electricity, relying on gravity and a profound understanding of hydrology. Roman concrete infrastructure not only endured for 2,000 years but actually grew stronger, healing its own wounds, while our modern counterparts are often designed with obsolescence in mind. The Minoans enjoyed advanced sanitation and plumbing that would not become standard again until the modern era, showcasing a commitment to public health that was woven into the very fabric of their cities. These were not primitive solutions, they were brilliantly adapted, long-term strategies for thriving within the limits of the natural world. So where do we go from here? The challenge these mysteries present is not to simply recreate a Roman vault or a Viking sunstone, but to embrace the spirit of inquiry and deep observation that made them possible. It is to look at the problems of our time with the same resourcefulness and respect for natural principles that our ancestors exhibited. By studying their successes and their failures, we can begin to reimagine our own relationship with technology, not as a means to dominate nature, but as a way to collaborate with it, to build a world that is not just advanced but enduring. The silent, enduring stones of Sacsayhuamon and the uncorroded iron of Delhi are not just relics, they are benchmarks calling on us to build a legacy worthy of the ones we have inherited. Thank you for exploring these profound enigmas of human history with us. This journey is a reminder that the past is not a closed book but an ongoing conversation, filled with voices that still have much to teach us. If this exploration sparked your curiosity, please share your own thoughts in the comments below. Which of these ancient technologies do you find most inspiring or most perplexing? For more journeys into the mysteries of our world, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an adventure. Until next time, keep looking back to find new